Hello there and welcome to Just About Earth, where curiosity gets comfortable and science takes its time. Tonight we are looking at something that sounds a little dramatic at first, perhaps even a touch suspicious, but turns out to be much more interesting than a simple mystery headline. We're talking about things on Earth that seem, at least on first inspection, as though they do not quite belong here. Not necessarily because they arrived from somewhere else in a flying saucer and parked badly, though I imagine that would simplify matters. No, what makes these discoveries so compelling is that they sit inside our world and yet don't fit neatly into the expectations we've built around it. A material appears where it should not be. A form of life thrives where life should be having a very serious complaint. An object turns up in the wrong layer, the wrong place, or with the wrong story attached to it. A pattern repeats for reasons no one can fully pin down. A piece of the planet behaves as though it missed the memo on how planets are supposed to behave. Before we get into any of that, I'd love to know where you're listening from tonight. Are you tucked up at home, halfway through a sleepless evening, out on a late walk, or listening from a place where the day has only just begun? And while you're there, have you ever found something in your own life that felt strangely out of place? Not in an alarming sense, more in that quiet, ordinary way. A single glove in the kitchen, a spoon in the bathroom, a screwdriver somehow ending up in the fridge. Not impossible, just wrong enough to make you stop and stare for a second and ask, now how on earth did that get there? If you enjoy this sort of slow wandering through the stranger edges of science, do give the video a like and maybe subscribe as well. It helps this little corner of calm find other people who enjoy learning about the planet without being shouted at by dramatic music every 14 seconds. And if tonight's topic keeps you awake for a bit longer than planned, at least you'll be awake with a decent question in your head, which is not the worst company to have. The idea that something on Earth might not belong here is the sort of phrase that immediately tempts the imagination to run off unsupervised. It has a way of making us think of lost civilizations, coded messages, impossible artifacts, and perhaps one extremely concerned geologist squinting at a rock and saying, "That is not what I ordered." But the real story is both more sensible and, in my opinion, much better. Because when scientists say that something is odd, out of place, unexplained, or difficult to reconcile with current knowledge, they are not usually saying that nature has broken the rules. They are saying that our rulebook may not be complete, and that is an important difference. Earth has not promised to be tidy for our convenience. It has not agreed to arrange all its chemistry, biology and geology into a neat display cabinet with labels facing forward. Earth is old, busy, layered, violent, patient, and full of processes that overlap, interrupt, erase, and rewrite one another. Things sink, rise, melt, crystallize, dissolve, mutate, fracture, compress, and get buried. Organisms adapt, minerals travel, signals get distorted, sediments carry stories from one place to another, heat alters matter, pressure alters it again. Time, which is very good at changing everything and very poor at leaving explanatory notes, then steps in and makes the whole business more complicated. So when we come across something that appears not to belong, the first task is not to leap to conclusions. It is to slow down and ask a better question. Not, what impossible thing has happened, but what assumptions are being tested here? That is where the real intrigue begins, because an anomaly is not simply a weird object on a table. It is a small disagreement between the world and our expectations of it. And those disagreements are often where science gets its most useful work done. In ordinary life, we're quite good at ignoring the things that fit. You probably didn't spend much time today marvelling at the existence of a spoon that behaved exactly like a spoon. No one gathers the family and says, "Come quickly. This kettle is boiled in a manner entirely consistent with the laws of thermodynamics." We notice friction. We notice the unexpected. We notice the thing that doesn't match the label on the box. Science is much the same. The results that align with what we already understand are valuable, of course, but the results that refuse to sit still are often the ones that open new paths, not always dramatic ones. Sometimes the revolution begins with a tiny irritation, a reading that won't go away, a mineral that should not have formed under those conditions, a microbe living in a place that looks less like a habitat and more like a punishment. There is also something very human about our use of the phrase "doesn't belong here." It sounds objective, but it often reveals more about us than about the object in question. To say that something does not belong is to assume we already know where things do belong. It suggests that our categories are settled, our maps are complete, our timelines are reliable, and our definitions are sturdy. And quite often, they are sturdy enough for practical purposes. But nature has a habit of pressing on the weak points in our certainty. It finds the corners where our categories blur. It produces exceptions, hybrids, leftovers, and edge cases. It does not seem especially interested in whether this is helpful. Take the idea of a material appearing where it should not. That sounds straightforward until you remember how much of Earth's history involves materials being transported, transformed, and reassembled over astonishing spans of time. A grain of sand may have had a far more eventful biography than most of us. A mineral crystal might record conditions from deep within the crust before being lifted, broken, and carried elsewhere. Metallic elements can concentrate under very particular circumstances, and if we do not yet understand all those circumstances, the end result can look almost rude in its refusal to make sense. Something that appears impossible under one model may turn out to be perfectly possible under a more detailed one, though usually after someone has spent several years looking tired in a laboratory. Then there is life, which has spent a very long time proving that it takes obstacles personally. Again and again, we build a picture of the limits within which living systems can function, and again life edges up to that limit, hops over it, and starts making itself comfortable on the other side. Too hot, too acidic, too salty, too dry, too pressurized, too dark, too chemically awkward, too nutritionally miserable. These are the conditions in which we are often tempted to say life should not be. And yet, in one extreme setting after another, something tiny and persistent is already there, dividing happily and getting on with it. It is enough to make one suspect that microbes possess a level of confidence the rest of us can only dream of. The same goes for objects that seem out of context. Sometimes these turn out to be misunderstood, misdated, misplaced, or wrapped in a very enthusiastic legend. Humans are excellent at telling stories about found things, and those stories can grow in ways that are not always helpful. A discovery gets reported, the report gets repeated, the repetition gets polished. A few details are dropped, a few are added, and before long an odd but manageable archaeological puzzle becomes an impossible artifact, according to 3 websites, 2 documentaries, and 1 man on the internet who appears to have very strong feelings about Atlantis. That is why context matters so much. Not just where an object was found, but how it was found, who documented it, what methods were used, what contamination is possible, what alternative explanations exist, and how much of the mystery survives once the dust is cleared away. That last point is important, because not every anomaly remains mysterious once it is studied properly. Some do fade under good scrutiny, and that is not a failure. That is science doing its housekeeping. It is how we separate truly useful puzzles from the ones assembled out of bad measurements, incomplete records, hopeful storytelling, or a rock that looked very suspicious until someone turned it over. There is a tendency, especially in popular discussions, to imagine that mystery is diminished by explanation. But the opposite is often true. When a weak mystery falls apart, it clears space for stronger questions. It gives us less nonsense to trip over. It leaves the genuine unknowns standing in clearer light. And the genuine unknowns are more than interesting enough. Earth is not merely the stage on which science takes place. It is also the things still being figured out. We know a great deal about this planet, more than any previous generation could have imagined, and still large portions of its story remain incomplete. We continue to revise timelines, redraw relationships, discover hidden ecosystems, rethink geologic histories, and refine the conditions under which matter and life can organise themselves. New instruments help, better dating methods help, deeper drilling, improved imaging, cleaner sampling, stronger models, and larger data sets all help. But even with all that, there are still findings that arrive with a stubborn little expression, as if to say, yes, hello, your current understanding appears to be missing a few pages. What makes that so compelling is not the promise of something supernatural or otherworldly. It is the reminder that the natural world is under no obligation to be fully understood on schedule. That can sound frustrating if you are hoping for a final answer before bed, but it is actually rather comforting. It means the world is still larger than our summaries of it. It means knowledge is not a finished warehouse, with all the boxes stacked neatly to the ceiling. It is an active work site. There are tools everywhere, people checking measurements, one person looking at a data set upside down, and every now and then someone in the corner saying, I know this sounds odd, but I've found something. And often that something is not flashy at all. It may be microscopic. It may be buried in strata. It may be a faint pattern in isotopes, a bizarre chemistry in ancient rock, an organism surviving in a place where there seems to be no business surviving, or a manufactured-looking object that appears to disrupt the sequence we expected. The attention it gets does not always match its size. Sometimes a very small anomaly creates a very large argument, which is a wonderfully human habit. We're quite capable of looking at one odd sample and producing several conferences worth of disagreement from it. This is why the most useful approach tonight is not to treat the phrase "doesn't belong here" as a conclusion. It is better thought of as a temporary label, a marker of tension, a way of saying, here is a discovery that has not yet been comfortably absorbed into the story we tell about Earth. That tension may eventually resolve into a new explanation. It may reveal contamination, error, exaggeration, or missing context. Or it may point towards something genuinely important about how our planet works. The point is not to dramatize the gap. The point is to take it seriously. There is also a deeper reason these cases hold our attention. They challenge a comforting instinct we all have, which is the instinct to think that the familiar world is basically settled, that the really big surprises happen elsewhere, out in distant space perhaps, on exoplanets with unpronounceable names, in the atmospheres of giant worlds, or under the ice of distant moons. We tend to imagine Earth as the known place, the catalogued place, the place where the labels have already been written. But Earth is still capable of producing astonishment, and not just in the obvious ways, not merely through volcanoes and storms and mountains, but through details, through inconsistencies, through discoveries that make experts pause and revisit the basics. It is a bit like living in a very old house and finding a locked drawer you never noticed before. The house is still your house. Nothing magical has happened to it overnight. But suddenly you are aware that your knowledge of it was partial. There were compartments. There were alterations made before you arrived. There are old decisions in the walls. Some parts were built over, some repaired badly, some improved cleverly, and some perhaps never fully understood in the first place. Earth is very much like that, except the house is around 4.5 billion years old, and the drawer occasionally contains microbes in boiling acid or minerals with a biography longer than mammal evolution. So as we settle into this investigation, it may help to loosen one assumption right away. The question is not whether Earth contains impossible things. It does not, at least not in the strict sense. The better question is whether Earth contains things that expose the limits of our current explanations, things that force us to sharpen our methods, check our confidence, and expand our models. Things that seem out of place only because the place itself is more complicated than we realized. That means we will need to be careful with language. Words like impossible, forbidden, alien, mysterious, and anomalous are tempting because they make a good entrance. But they do not all mean the same thing, and the distinctions matter. A discovery can be surprising without being inexplicable. It can be poorly understood without being miraculous. It can challenge one theory without threatening all of science. In fact, the best scientific mysteries are usually very specific. They do not wave their arms and shout that everything is wrong. They simply sit there, calm as you please, and refuse to match the expected pattern, which is, in its own way, much more persuasive. And there is another small comfort in all of this. We do not need the planet to become stranger in order for it to be interesting. It already is. The more closely we look, the more apparent it becomes that normal Earth is full of behaviour we once would have called extraordinary. Entire ecosystems beneath the seafloor, organisms that metabolize in ways once thought implausible, geological structures whose history takes pages to explain properly, ancient materials preserving evidence of conditions that no longer exist. It is not that reality has suddenly become weird. It is that our view of normal has been expanding and will likely continue to do so. So tonight we begin with that small but useful shift in perspective. When something on Earth appears not to belong, we are not necessarily looking at a violation of nature. More often, we are looking at an invitation to ask how it formed, how it got there, what conditions made it possible, what assumptions it disrupts, and whether the oddity lies in the object itself or in the limits of the framework we brought to it. Once you start looking at anomalies that way, they become less like intruders and more like clues. And with that in mind, we can start moving from the idea of the misplaced thing to the kinds of discoveries that earn that description in the first place, beginning with some of the most basic and stubborn evidence of all, the materials themselves and the quiet ways certain stones, metals and mineral traces manage to tell us that Earth still has a few habits we do not fully account for. Rocks do not usually advertise themselves as troublemakers. They sit there looking dependable, which is probably why we trust them so much. A tree may rot, an animal may run off, a cloud may entirely fail to commit to a shape, but a stone gives the impression that it has made peace with being a stone and intends to remain one for the foreseeable future. That is part of what makes geology feel so reassuring. It deals in things that seem solid, slow, and obedient. Granite behaves like granite. Basalt behaves like basalt. Sandstone does what sandstone has always done, which is mostly sit there and become part of a wall in a very old village if given the chance. And yet, every so often, a rock turns up with the geological equivalent of a fake moustache and no paperwork, and suddenly the whole business becomes much more interesting. The reason stones can be so disruptive is that they are not merely lumps. They are records. A mineral crystal is not just matter in a tidy shape. It is a piece of evidence about pressure, temperature, chemistry, depth, time, and movement. It tells you where it formed, or at least where it prefers to form. It tells you something about the environment it came from and the journey it survived. Most of the time, those stories line up reasonably well with what we expect. A volcanic rock suggests heat and eruption. A sedimentary layer suggests transport and settling. A metamorphic mineral suggests burial, pressure, and a fairly hard life underground. Geologists like that sort of thing. It is orderly. It has cause and effect. You can build a very respectable career on a mineral that behaves itself. But when a stone contains a mineral phase that should only exist at absurd pressure, and you find it in a mountain belt near the surface, that is when the eyebrows start to move. When a tiny crystal survives from the first few 100 million years of Earth's history, and seems to suggest that the young planet cooled earlier than expected, that is when established timelines begin to look less secure. When a strange black diamond turns up in only 2 distant parts of the world, with properties that do not sit comfortably inside the usual diamond story, geologists begin speaking in the special tone scientists use when they are trying to sound calm while privately enjoying the chaos. A good place to begin is with a stone that was not supposed to be there, at least not in that condition. One of geology's more humbling discoveries involved minerals such as coesite and stishovite, both high-pressure forms of silica. Now, Silica itself is not exotic. It is one of the most common ingredients in Earth's crust. Quartz is silica. Sand is mostly silica. Plenty of kitchen counters are, in spirit if not in geological pedigree, proud descendants of silica. But coesite and stishovite are different arrangements of the same atoms, packed into structures that require far more pressure than ordinary crustal conditions usually provide. For a long time, minerals like these were associated with meteorite impacts or very deep environments. They were the sort of things you expected from violent compression, not from the sort of continental rocks people hike across in sturdy boots and mild weather. And then geologists found them in metamorphic rocks from mountain belts, which was awkward in the best possible way, because if those minerals were really what they appeared to be, then those rocks must once have been buried far deeper than many earlier models allowed. Not gently tucked away for a while, properly dragged down into the mantle, squeezed at tremendous pressures, and then somehow brought back up again without entirely forgetting where they had been. That was not a trivial adjustment. It meant continents were capable of being subducted to depths once thought much less likely, then exhumed again through processes so slow and forceful that a mountain range could effectively serve as a return address. There is something wonderfully rude about that sort of mineral evidence. Entire theories can sit around looking confident until one little crystal says, "Actually, no, this rock has been to places your model does not account for." It is a bit like finding a boarding pass in someone's coat pocket after they have spent the week insisting they never left town. The coat may look ordinary, the person may look ordinary, but the evidence says otherwise. This is one of the reasons geology can be much stranger than it first appears. We tend to imagine rocks as local. A cliff belongs to its cliff, a mountain belongs to its mountain, but the minerals inside that rock may have had a much more adventurous history. Some have been buried to extraordinary depths. Some have been melted, recrystallized, fractured, reburied, and uplifted. Some carry remnants of environments that no longer exist at the surface at all. They are less like static objects and more like reluctant memoirists. Then there are zircons, which are tiny, stubborn, and quietly magnificent. Zircon crystals are not impressive in size. You could lose one on your fingertip and spend the next hour wondering whether science had always been this uncooperative. But zircons are famously durable. They resist weathering, survive recycling through multiple rock cycles, and most importantly for geologists, they can preserve uranium and lead in ways that allow extremely precise age dating. If rocks are witnesses, zircons are the ones who keep receipts. Some of the most famous zircons on Earth come from Jack Hills in Western Australia, and what made them so startling was not just that they were old, but how old. These crystals push back into the very early history of the planet, close to the Hadean Eon, a time long imagined as blisteringly hostile, heavily bombarded, and not terribly interested in making conditions comfortable for crust, oceans, or anything remotely civilized. The early Earth had a reputation. It was widely pictured as a place of magma, violence, and prolonged planetary bad temper, which, to be fair, it probably was in many respects. But some of these zircons hinted at something more nuanced. Their chemistry suggested they may have formed in the presence of liquid water and relatively cool crustal processes much earlier than many had assumed. That was a striking possibility, because if those interpretations were right, then Earth may have settled down, at least in patches, sooner than expected. Not completely. Not into a pleasant cottage garden with ferns and birdsong. Let us not get carried away. But perhaps into a world capable of crust, water, and geochemical cycles more quickly than the old hellish stereotype allowed. Once again, the rule had not exactly been broken by nature. It had been broken by our assumptions about how long young planets remain geologically chaotic. It is hard not to enjoy the scale of that correction. A crystal smaller than a grain of rice helping revise our picture of the early Earth is exactly the kind of thing science should contain more often. Whole narratives about planetary youth, magma oceans, and crust formation become less certain because a tiny mineral held onto isotopic clues for more than 4 billion years. That is either inspiring or deeply annoying depending on whether you are the theory being revised. And then, of course, there are diamonds, which have a talent for complicating matters even before they become jewellery. In ordinary conversation, diamonds are treated as luxury objects with a mildly exhausting social life. In geology, they are pressure capsules. They form deep within the earth and can trap tiny inclusions inside them as they grow, preserving fragments of the environment in which they formed. That makes them extraordinarily useful. It also makes them capable of delivering awkward news from the mantle. One of the most remarkable examples came in the form of ringwoodite, a high-pressure mineral phase associated with the mantle transition zone, hundreds of kilometres below the surface. Ringwoodite had been known from meteorites and laboratory experiments, but finding it as an inclusion inside a diamond was something else entirely. Because that meant a real sample of transition zone material had effectively been carried upward in a crystalline armoured vehicle. Even more importantly, that ringwoodite contained water in its structure, not as sloshing underground lakes in the way people sometimes imagine, but as hydroxyl bound into the mineral itself. That discovery gave strong support to the idea that vast quantities of water may be stored deep within Earth's interior, locked into minerals rather than sitting in open reservoirs. Now, that is not the kind of water story that makes for dramatic newspaper illustrations. No one gets to point at an underground ocean the size of a continent and say, there, that one. But scientifically it was huge, because it suggested the deep Earth is not simply a dry mechanical engine. Water in chemically bound form may be cycling through far deeper parts of the planet than many non-geologists had ever considered, influencing melting, viscosity, and the movement of material over immense timescales. A diamond formed under crushing pressure and blasted upward by volcanic processes had carried evidence from a region humans will never visit and reported back with very little fuss. Other diamonds have preserved inclusions of minerals stable only under extreme depth, and some have even contained tiny pockets of high-pressure ice phases, which sounds so unreasonable the first time you hear it that you're tempted to ask someone to repeat themselves more carefully. Ice, in most people's minds, belongs in freezers, winter fields, and disappointing drinks. Yet under enormous pressure, water takes on crystal structures unlike the ice in your kitchen. Finding evidence of such phases trapped within deep origin diamonds tells us again that the mantle is chemically and physically more varied than the simpler textbook image of a uniformly hot interior might suggest. Stones, once again, refusing to stay in their assigned category. If diamonds are elegant messengers from depth, Carbonado diamonds are the eccentric relatives at the edge of the family photo. Carbonado, often called black diamond, is unlike the clear crystal form most people picture. It is polycrystalline, porous, dark, and structurally odd. It occurs significantly only in Brazil and the Central African Republic, which is already a rather specific arrangement if you are hoping for a tidy global explanation. It also tends to be old, inclusion poor in the usual sense, and difficult to fit comfortably into the standard model of diamond formation in the mantle. Over the years, Carbonado has inspired a range of hypotheses. Some researchers have suggested unusual mantle processes. Others have looked at giant impacts. Some discussions have wandered all the way into extraterrestrial ideas, suggesting formation in space before arrival on Earth, though that remains controversial and not at all settled in the way people on dramatic television enjoy implying. The important point is not that Carbonado proves anything fantastical. It is that it sits awkwardly in the catalogue. Its texture, chemistry, distribution and origin story do not line up as neatly as geologists would like. It is the geological equivalent of finding an antique key in your coat pocket when you're quite sure you have never owned a chest. And then there is moissanite, a mineral made of silicon carbide, which for a long time carried its own sort of improbability. Silicon carbide is common enough in industrial contexts and known from meteorites, but under normal oxidizing conditions near Earth's surface, it is not what you would expect to form naturally and casually in terrestrial rocks. So when natural moissanite began turning up in certain geological contexts, especially associated with unusual mantle-derived materials, it raised questions about the chemical environments involved. How reducing were those conditions? What does that tell us about specific pockets of the mantle? What pathways allowed such a mineral to form and survive? Again, the mineral itself was not violating nature, it was violating expectation. It implied that Earth contains localized conditions much more chemically extreme and varied than a simple average model would suggest. This is a recurring theme with so many of these so-called rule-breaking stones. The problem is often not the stone. The problem is the comforting idea that the Earth's interior ought to be uniform enough to summarize easily. Perhaps that is why natural quasi-crystals caused such a stir. Before they were found in nature, quasi-crystals were already famous for upsetting crystallography. Ordinary crystals repeat in regular patterns. That repetition places limits on the symmetries they can display. Quasi-crystals broke that expectation by showing ordered structures without conventional periodic repetition, allowing symmetries once thought impossible in crystals. For a while they sounded like the kind of thing nature ought not to make, which is usually an excellent way to tempt nature into making exactly that. Eventually naturally occurring quasi-crystals were identified in material from the Katurka meteorite, found in Russia. Strictly speaking, that gives them an extraterrestrial origin, so they are not Earth-made in the usual sense. But they were found on Earth, studied on Earth, and served as yet another example of matter, turning up in a form that had once been dismissed as impossible outside a laboratory or theoretical curiosity. If the phrase "doesn't belong here" ever needed a careful footnote, that would be one of the cases. Not because the material was magic, but because our categories had lagged behind reality. That is often the pattern with stones that seem to break rules. The stone arrives first. The explanation arrives later, if it arrives at all. Between those two moments lies the interesting part. The measurements get checked. The crystal structure is tested. The isotopes are examined. The pressure-temperature conditions are modelled. Scientists argue politely in papers and less politely over coffee. Alternative explanations get proposed. Some fade, some strengthen. And gradually the strange stone stops being an intruder and starts becoming a clue. It is worth lingering on that because there is a temptation, whenever a geological anomaly appears, to imagine that the main drama lies in whether it is real. But usually the more useful question is what kind of real it is. Is it evidence of deep subduction, ancient crust, extreme redox chemistry, impact conditions, mantle fluids, early planetary cooling, unusual transport histories? A rock can be fully real, fully natural, and still deeply disruptive to current models. In fact, those are often the most valuable cases. The ones that do not collapse into fraud, contamination, or misunderstanding, but remain standing as little factual inconveniences. And there is another thing stones do very well. They remove our sense of scale. A cliff may look ancient, but a zircon inside it can be older than the rock around it. A diamond in a ring may seem ornamental, but as a geological object it is a survivor from crushing depths, carrying inclusions from realms inaccessible to direct study. A mountain path may cross rocks once buried far deeper than the height of the mountain itself. A black pebble may contain an origin story still being argued over decades after its discovery. Beneath the ordinary appearance of stone lies an unnervingly large amount of history. That makes geology less about scenery and more about translation. The world is full of material statements, and we are still learning how to read them. Some are straightforward, some are badly smudged. Some appear to say one thing until a new instrument reveals they were saying something else all along. And a few say, very plainly, that Earth has been doing things more complicated than our current explanations can easily summarize. So when we speak about stones that broke the rules, what we really mean is stones that expose the limits of older rules. They are reminders that geology is not a finished filing cabinet, with every mineral in its correct drawer. It is an active investigation into a planet that keeps reworking its own evidence. Rocks melt and reform. Crust dives and rises. Water enters places we did not fully appreciate. Minerals preserve conditions no human will ever witness directly. Tiny crystals outlast oceans, mountain ranges, and theories about both. And if that makes the ground beneath us feel slightly less settled than before, that is probably a fair response. Not because the Earth is unstable in some immediate dramatic way, but because its history is far less tidy than the labels in school diagrams suggest. Stones look quiet, but many of them are carrying scandalous amounts of information. Once you begin to notice that, it becomes harder to think of metal as simple either. Because the same planet that hides impossible-seeming stories in crystals and diamonds also leaves behind stranger traces in its ores and native elements, as though the chemistry itself has been writing side notes in the margins. If stones are the quiet archivist of the planet, metals are the clues that never arrive with enough context. A mineral crystal may tell you about pressure and temperature. A sediment layer may tell you about water, wind, and time. But a metal, especially when it turns up in a strange form or strange place, tends to provoke a more immediate kind of suspicion. Because metals are not supposed to be casual. Earth does not generally leave them lying around in pure, convenient, gleaming forms as though the crust was some sort of absent-minded workshop. Most metals on this planet are chemically sociable to the point of inconvenience. They bond with oxygen, sulfur, chlorine, carbon, silicon, and whatever else is available. They get folded into minerals, dissolved in fluids, trapped in ores, scattered in trace amounts, or locked into compounds that require considerable effort to separate. So when a metal appears in a form that seems too pure, too concentrated, too oddly placed, or too difficult to explain, it has a way of making geologists look at the landscape as though the ground itself may have skipped a few steps. That is part of what makes metal so intriguing in a discussion like this. A strange stone may be confusing, but at least rocks are expected to be there. Metals, especially the ones we think of as refined, useful and industrial, carry a different emotional weight. They feel like products, they feel processed, they feel as though they ought to emerge from furnaces, not from mountain fractures or volcanic deposits or black sand on a riverbank. And even when we know perfectly well that metals are natural, there is still something unsettling about encountering them in forms that seem to bypass the neat chemical logic we rely on to explain their behaviour. This is because the Earth's surface is, in broad terms, not a friendly place for many pure metals to remain pure for long. Oxygen sees to that. Water helps. Time is happy to assist. Iron rusts. Copper tarnishes. Reactive metals bond readily and disappear into compounds. Gold, which is famously reluctant to react with almost anything, can survive in native form and has therefore spent thousands of years convincing human beings to lose their composure. But many others are not so accommodating. So when nature produces native metal, meaning metal in a relatively pure elemental state, it often implies highly specific conditions: reducing environments, unusual temperatures, special chemistry, transport by fluids, rapid isolation. A sequence of events precise enough that the final result looks less like the default state of the planet and more like a very narrow success. That is where the phrase, "no obvious story," becomes useful. Because in geology, a discovery rarely needs to be impossible to be disruptive. It simply has to resist the first three explanations. If a geologist sees native copper, there are pathways to account for it. If they see native gold, again, the world has several ways of arranging that. But if they see native iron in a terrestrial rock, and there is no immediate sign of meteorite contamination, that is a much more interesting moment. Not because iron cannot exist as metal, but because on Earth's surface and in ordinary crustal conditions, it usually does not get to remain that way. It prefers, if preference can be assigned to iron, to become part of oxides, silicates, sulfides, and a whole catalogue of minerals that sound much more stable and much less dramatic. This is why native iron on Earth has such a peculiar reputation. Most iron we encounter in truly metallic form in natural settings has an extraterrestrial biography. Meteorites bring it in. Iron-nickel alloys survive the journey, hit the surface, and there it is. A chunk of metal that seems almost too straightforward to have come from nature at all. For a very long time, that helped reinforce a quiet assumption. Metallic iron belongs to space. Oxidized iron belongs to Earth. Not as an absolute rule, but as a very comfortable general one. Then geology, as it often does, began providing exceptions. One of the most famous examples comes from Disco Island in Greenland, where large masses of native iron occur in basaltic rocks. This was not a minor inconvenience to expectation. Basalt is volcanic rock, rich in iron-bearing minerals, yes, but not usually the place one expects to find substantial metallic iron sitting around as though a foundry had taken a wrong turn. The explanation that emerged was not simple, but it was elegant. Basaltic magma interacted with carbon-rich sediments, including coal-bearing material, under reducing conditions. That interaction stripped oxygen from the iron compounds and allowed metallic iron to form. In other words, the metal was not appearing without reason. It was appearing because the local chemistry had become strange enough and reducing enough to permit what would otherwise seem highly unlikely. That kind of explanation is satisfying because it turns an apparent impossibility into a more complex natural story. But it also does something slightly more interesting. It expands the range of circumstances under which the Earth can surprise us. Once you know that a volcano intruding into the right kind of carbon-rich sediment can manufacture native iron, you do not just solve one puzzle. You start looking differently at how magmas interact with their surroundings. You start asking what other highly localized chemically extreme environments may exist or may once have existed, and you become a little less confident that the planet always behaves in the averaged textbook way. There is something almost mischievous about that. We build broad chemical expectations because they are useful and largely correct. Then Earth produces a local exception, and reminds us that a planet is not an average. It is a patchwork of conditions, histories, and accidents. The average Earth may oxidize iron. A specific Earth, at a specific site, in a specific geological moment, may do something else entirely. Native copper has its own version of this story, though in a less chemically shocking form. Copper, unlike iron, can persist more readily in native form under the right conditions, and there are regions where truly enormous deposits of native copper occur. The Kuinor Peninsula around Lake Superior is perhaps the classic example. There, native copper appears in basalt-hosted systems in masses so substantial that early miners found not just grains or veins, but gigantic lumps. This was a gift to human technology, though perhaps a mixed blessing to anyone tasked with moving several tons of metal using 19th century equipment and an optimistic expression. The scientific interest, however, lies in how that copper got there. Copper does not simply decide to gather itself into large metallic masses for aesthetic effect. It needs to be transported, concentrated, and precipitated. Hydrothermal fluids move through rocks carrying dissolved metals. Changes in temperature, pressure, pH, sulfur content, and oxidation state influence what stays in solution and what drops out. Basaltic sequences, fractures, fluid pathways, burial, and later tectonic histories all matter. In other words, even when a native metal deposit is explicable, the explanation is a chain, not a sentence. And if any link in that chain is poorly understood, the deposit can seem unreasonably abundant, oddly pure, or strangely placed. Gold is perhaps the most emotionally overqualified example of all this. Human beings see gold and immediately forget to behave normally, which is a problem if one is trying to discuss hydrothermal transport with a straight face. But scientifically, native gold is fascinating precisely because it appears in ways that are both explainable and deeply variable. Gold can be transported in hydrothermal fluids under specific chemical conditions, often as chloride or sulfur complexes, then precipitated when those conditions shift. It can end up in quartz veins, shear zones, altered rocks, and placer deposits downstream, where weathering and water have concentrated dense particles over time. None of that is supernatural, but the details are difficult, and for a long time certain concentrations seemed almost too efficient, as though the crust had developed a private financial strategy. The deeper question behind deposits like these is not whether metals can occur naturally. They can. It is how they become separated from the massive background clutter of the crust. Most crustal rock is not ore. It contains useful elements, yes, but in concentrations too low or too scattered to matter much. To produce an ore body, geology has to act like a selector. It has to take one ingredient among many and gather it. Not perfectly, not neatly, but enough to make the result striking. That selection requires processes, and when those processes are incomplete in our models, the deposit looks as though it appeared with no obvious story. There are entire classes of deposits that have forced this kind of rethinking. Layered mafic intrusions, for instance, can concentrate chromium, platinum group elements, vanadium, and magnetite in patterns so regular and extensive that they almost look manufactured. Great sheets of magma cool slowly in the crust, and different minerals crystallize at different stages. Those minerals settle, accumulate, react, and sometimes segregate valuable metals in astonishing quantities. The Bushveld complex in South Africa is one of the grand examples, a geological structure so vast and so metallurgically important that it feels less like a local anomaly and more like the Earth briefly taking industrial design into its own hands. Yet even here, the details have been debated for years. How much is crystal settling? How much is fluid movement? How much is replenishment by new magma pulses? How do sulfide liquids separate and scavenge metals so efficiently? The broad framework is solid. The fine-grained story remains complicated, and then there are the metals that seem to form where they should hardly be able to. Platinum group elements, for example, are not common companions in everyday rock. They are siderophile, iron-loving elements, and much of Earth's original inventory is thought to have followed iron into the core during planetary differentiation. So why do we have accessible platinum, iridium, osmium, and their relatives in the crust at all? Part of the answer may lie in incomplete segregation, mantle processes and later concentration, while part touches on a much larger planetary story involving late accretion, the addition of material after core formation. Even here, what looks like a local metal question opens outward into the earliest assembly of the planet. A metal deposit in the crust can end up being a clue, not just about fluids and magma, but about what struck Earth billions of years ago and what was left behind. This is one of the recurring pleasures of geology. You begin with a nugget and end with planetary formation. The scale refuses to behave. There are also the seafloor metals, which introduce a different kind of discomfort. Manganese nodules and cobalt-rich crusts do not look dramatic at first glance. They look like something you would kick by mistake on a wet beach and then politely ignore. But scattered across parts of the deep ocean floor are nodules rich in manganese, iron, nickel, copper, cobalt, and rare earth elements, growing at rates so slow that watching paint dry would count as reckless excitement by comparison. Millimeters over millions of years. That sort of growth asks a lot of one's patience, and yet those nodules accumulate in extraordinary abundance over vast seafloor regions, pulling useful metals out of seawater and sedimentary pore waters with an efficiency that is still the subject of active study. Their story is not absent, but it has long been incomplete. Why do nodules grow where they do and not elsewhere? Why do some layers enrich certain metals more effectively than others? How do microbial processes interact with purely inorganic precipitation? How stable are the conditions over the timescales required? Once again, the metal is not impossible. The system is just more subtle than it first appears. A slow chemistry, a vast surface, a deep ocean setting with unusual redox behaviour, and suddenly the seabed begins behaving like a patient collector. There is something almost comical about the contrast. Humans build refineries, smelters, separation plants, and electrochemical systems to coax useful metals into concentrated form. Meanwhile, the Earth, given enough time, pressure, fluid pathways, and a frankly unreasonable tolerance for waiting, produces ore bodies, native metals, and seafloor metal accumulations on its own. Not always where we expect, not always by the route we first assume, but often enough to remind us that industrial logic is, in some ways, an imitation of geologic logic under more hurried management. One particularly unsettling category involves metals associated with environments that ought to destroy the very form in which they appear. Strongly oxidizing conditions, weathered settings, hydrothermal alteration zones, and sedimentary environments full of reactive chemistry should, on paper, leave little room for certain native phases to survive. And yet microscopic studies sometimes reveal tiny grains of elemental metals or alloys in places where standard geochemical intuition would not put them first. Some can be explained by contamination, analytical error, or highly localized reduction. Others remain hard to place. The modern tendency is to be careful, which is wise. Tiny grains are easy to misread, and extraordinary claims about native aluminum, silicon, or iron in odd settings have a way of attracting more enthusiasm than they deserve. But even the cautious cases reinforce the same lesson. Local geochemistry can produce pockets of behaviour far stranger than the average environment would suggest. It helps to remember that rocks are not closed boxes. Fluids move through them, gases move through them, heat pulses through them, organic matter interacts with them, faults open and seal, minerals dissolve and reprecipitate, oxidation fronts advance, reducing zones linger. Tiny cracks become highways if you wait long enough. A metal found in the wrong place may not actually have formed there in the simplistic sense. It may have travelled, been stripped from solution, remobilized, concentrated again, and finally isolated in a setting that hides most of its history. By the time we arrive with a hammer and a notebook, the last step is visible and the first 6 are gone. That missing context is what makes metallic anomalies feel so suggestive. They sit at the boundary between chemistry and story. A pure metal grain is not just matter. It is a statement that a specific sequence occurred. If we cannot reconstruct that sequence, the metal feels almost suspicious, as though it has arrived without provenance. But provenance is often what geology is worst at preserving in a simple, readable form. Events overwrite one another. Ore bodies are metamorphosed. Tectonics shuffles terrains. Weathering removes key textures. Mining destroys context in the very act of revealing value. The result is that some of the most significant metal deposits on Earth are understood in broad outline, but still argued over in detail, which is a very scientific way of saying that everyone agrees something happened, but the exact choreography remains annoyingly unclear. And perhaps that is why metals inspire such strong reactions in these conversations. They are both familiar and unnatural seeming. We use them every day, but only after enormous processing. So when Earth presents them in concentrated, native, or chemically surprising forms, it feels as though the planet has done part of the work in secret. It feels almost backstage. We are seeing not just raw material but a result. And results make us ask for method. Sometimes that method is beautifully specific. A reducing magma-sediment interaction here. A hydrothermal fracture network there. A sulfide melt scavenging platinum group elements from a giant intrusion. A sedimentary basin concentrating copper through redox boundaries. A deep ocean nodule growing one impossible fleck at a time for millions of years. In each case, the story exists. It is just rarely obvious from the object alone. That may be the real pattern emerging here. Things on Earth do not usually not belong in any absolute sense. Rather, they belong to a process we have not fully reconstructed yet. The metal is not the intruder. The metal is the surviving clue after most of the explanation has been weathered away. And because metals are so sensitive to chemistry, oxidation state, fluid history, and deep planetary sorting, they're especially good at exposing the fact that Earth is still not fully legible to us. So when a metal turns up with no obvious story, the temptation is to think the world has produced something anomalous. More often, the world has produced something entirely natural and then hidden the steps so well that the result looks almost too convenient, too concentrated, or too chemically improbable to trust at first glance, which makes these discoveries less like violations and more like missing paragraphs. The sentence is there, the ending is there, we simply do not have all the middle, and that missing middle matters for more than geology. Because once you accept that the planet can create materials and concentrations that seem to outrun our neat expectations, it becomes easier to understand why Earth can also support forms of life in settings we once thought completely unworkable. The chemistry prepares the stage long before biology walks onto it, and in some of the harshest places where metals gather, react and circulate in ways that seem initially unreasonable, life has found equally unreasonable ways to persist. That is where things become especially difficult for our instincts, because most of us carry around a fairly narrow image of where life belongs. We imagine forests, coastlines, grasslands, riverbanks, coral reefs, perhaps a respectable garden if somebody has remembered to water it. Even when we think of tougher environments, we still tend to picture life within a certain range. Cold but not ridiculous, hot but not boiling, salty but not enough to make a chemist raise an eyebrow. Acidic perhaps, but not to the point where your first concern would be whether your boots are dissolving. Somewhere with sunlight, some oxygen maybe, some water, in a form that looks reasonably water-like, and conditions that would not cause the average houseplant to file a formal protest. That image is understandable. It is also incomplete. One of the most important lessons modern biology has taught us is that life is not merely present where conditions are comfortable for us. It is present across a much wider range of temperatures, pressures, acidities, salinities, and chemical settings than people once thought possible. Not always in the form of large, obvious organisms with expressive eyes and excellent public relations. More often as microbes, mats, films, colonies, and communities so small or so strange that they can be missed entirely unless someone goes looking with patience and equipment. But once found, they force a reconsideration of what habitable means. And this is precisely the sort of discovery that can make something on Earth seem as though it does not belong here. Not because the organism is alien, but because the setting appears so deeply unwelcoming that the mind resists the pairing. We look at a superheated vent fluid, an acid mine drainage stream, an underground brine cut off for millennia, a salt flat, a subglacial lake, a radioactive waste site, or a pore space kilometres beneath the surface. And our first reaction is usually not, yes, perfect, that looks ideal for a thriving biosphere. Our first reaction is generally something closer to, well, certainly not there. But certainly not there has become one of the least reliable phrases in environmental microbiology. Part of the reason is that biology has spent decades escaping the categories we tried to place around it. For a long time, the study of life was guided by examples that were easy to see, easy to culture, and easy to classify using familiar environments. Lakes, soils, animals, plants, fungi, ordinary bacteria growing in labs under conditions that were, from the microbe's perspective, almost embarrassingly accommodating. As our methods improved, however, we began finding organisms in places that had not been treated as habitats at all. Some were merely overlooked, others were genuinely difficult to investigate. The result was not a small extension of life's boundaries, but a considerable one. A classic example is the world of hydrothermal vents on the deep sea floor. These are places where seawater seeps into the oceanic crust, is heated by underlying magma, reacts with rocks, and then rises back out carrying dissolved minerals and reduced chemicals. The fluid can be extremely hot, the pressure is immense, the sunlight is entirely absent, and the chemistry is unlike anything in a pleasant coastal tide pool. By the standards of everyday intuition, this is not a place to set up a food web. It is a place to lose a submarine glove and have an interesting insurance conversation. and yet hydrothermal vent systems host complex communities. Tube worms, mussels, shrimp, crabs, microbes, entire ecosystems structured not around photosynthesis, but around chemosynthesis. Instead of sunlight powering the base of the food chain, microbes use chemical energy from compounds such as hydrogen sulfide or methane. This was not just a curious exception, it was a conceptual shift. It showed that abundant life could exist in complete darkness, anchored to geochemistry rather than sunlight, and that the Earth's habitable space included environments we had barely considered. The deep ocean floor was not merely a graveyard for sinking organic debris. In places, it was biologically productive in its own right. That discovery did not mean that life ignores physical limits. It still has them. Proteins denature, membranes fail, DNA breaks, water behaves differently under extremes, chemistry pushes back. But the limits are broader and more flexible than older assumptions allowed, especially when evolution has had time to tailor cells to narrow, intense conditions. Thermophils and hyperthermophils, for instance, are organisms that live at high and very high temperatures. Some archaea and bacteria can grow at temperatures that would make most familiar life forms stop negotiating entirely. Their proteins are stabilized in ways that ordinary enzymes are not. Their membranes are adapted. Their molecular machinery is tuned to conditions that would destroy other cells. To them, a hot spring we regard with caution may be perfectly ordinary real estate. This is one of the reasons the phrase life where life should fail is more useful than impossible life. The life is not impossible. It is specialized. It is not breaking biochemistry. It is using biochemistry in ways that reveal how much range natural selection can explore. Once a lineage finds a niche and survives there long enough, evolution begins refining the details. Stability improves, repair systems strengthen, metabolism adjusts. The environment that looks uninhabitable to us becomes, for that organism, simply the local standard. Acidic environments offer some of the most dramatic examples. There are microbial communities living happily in waters with pH values so low that the liquid resembles something better suited to cleaning rust than supporting life. Acid mine drainage sites, volcanic acid springs, sulfur-rich pools, and naturally acidic rivers can host acidophils that not only tolerate those conditions but depend on them. Their cell membranes and transport systems are adapted to keep internal chemistry under control despite the very aggressive external environment. They do not so much conquer acidity as carefully manage the constant assault of it, which is an impressive way to make a living if a slightly stressful one. At the opposite end are alkalophils, which prefer highly alkaline conditions that would again be deeply inconvenient for most organisms. Then there are halophiles, which thrive in very salty environments. Salt lakes, saltons, brines, evaporate ponds and hypersaline sediments can hold dense microbial populations. Some produce pigments that turn whole bodies of water pink, red or orange, which is one of those moments where biology briefly acquires a flair for decoration. High salt is a problem for cells because it pulls on water balance and interferes with molecular function. Yet halophiles solve it through compatible solutes or specialized ionic strategies that allow their machinery to keep working. What would dehydrate or disrupt other life becomes their preferred condition. The same pattern appears with pressure. The deep sea is not just dark and cold in many places, it is crushingly pressurized. Every descent adds more water overhead, more weight, more force pressing into every structure. For surface organisms, that is a severe problem. For piezophiles or barophiles, it is simply home. Their proteins, membranes and cellular systems function properly under pressures that would make surface biology falter. Remove some of that pressure too abruptly and the cells may struggle, which is a wonderfully humbling inversion of perspective. What we think of as normal pressure is, for some organisms, not normal at all. Cold environments tell a similar story. Permafrost, polar sea ice, subglacial lakes, high mountain soils, and ancient frozen sediments all contain microbial life capable of persistence and sometimes activity at very low temperatures. Psychrophiles adapt by keeping membranes flexible, enzymes functional, and ice damage limited. In sea ice, tiny brine channels create microhabitats. In permafrost, cells may remain metabolically active at very slow rates, or endure long periods with minimal activity, ready to resume when conditions permit. Once again, life does not necessarily vanish at the edge of comfort. It retools. This matters because for a long time, many of these places were treated as marginal or empty by default. Too hot, too cold, too dark, too deep, too salty, too acidic, too isolated. The assumption was not irrational. It was based on what was then known. But each new environment that yielded life began eroding the old map of habitability. It became clear that Earth's biosphere was not limited to a thin, sunlit, temperate skin. It extended downward, sideways, under pressure, under ice, into rock, and into chemical regimes that did not resemble the settings in which biology had first been most intensively studied. The subsurface biosphere is perhaps one of the most striking examples. We tend to think of life as something on the surface or near it. Plants in soil, animals in water, microbes in sediments, roots in the top layers, sunlight somewhere in the story. But microbes exist deep underground, in fractures, pores, aquifers, rocks, and sediments far below the reach of light. Some live off chemical energy produced by water-rock interactions. Some feed on hydrogen, sulfur compounds, iron, methane, or other geochemically generated materials. Some are astonishingly slow-growing, existing in energy-limited conditions that make a sleepy afternoon seem like reckless acceleration. There are habitats deep below the surface where the question is not how life thrives flamboyantly, but how it persists at all, and yet persist it does. The deep biosphere may contain a significant fraction of Earth's microbial biomass, much of it largely out of sight and out of daily imagination. This is a profound change in how we think about the planet. The Earth is not just inhabited on top, it is inhabited within. One especially interesting case involves water isolated underground for extremely long periods, where microbial communities appear to survive on energy sources entirely disconnected from recent photosynthesis. In some deep fractures and ancient fluids, radiolysis of water, the splitting of water molecules by radiation from surrounding rocks, can generate hydrogen oxidants that provide usable chemical gradients. That is an extraordinary sentence to exist in ordinary biology. Life supported in part by the slow radiation-driven chemistry of rock and water deep underground. It sounds at first like something devised to make a very niche conference more exciting, but it is simply another reminder that if you give chemistry enough time, life enough opportunity, and evolution enough patience, pathways open where we did not initially expect them. Caves provide a quieter version of the same theme. Some cave systems host ecosystems with little or no direct sunlight, relying on organic matter washed in from outside, on microbial chemosynthesis, or on bizarre local chemistry. In certain sulfidic caves, microbes form the base of food webs using sulfur compounds rather than light. The cave walls, streams, and air-water interfaces become surfaces of microbial productivity. In other systems, organisms evolve in long isolation, losing pigment and eyesight because those features no longer matter. That is not life barely clinging on. That is life becoming so settled in the dark that it begins remodeling itself around it. Even deserts, which look empty at first glance, are less empty than they appear. Dry valleys, salt crusts, rocks in high radiation environments, and hyper-arid soils can all harbour microbial communities. Some live inside rocks as endoliths, using the thin protection the mineral matrix offers against ultraviolet radiation and desiccation. Others become active only when brief moisture appears, then return to dormancy with impressive efficiency. We often treat dryness as an obvious barrier, and of course it is a serious one. Water is not optional. But life has evolved ways to survive long interruptions, to use tiny films of moisture to endure salt stress and to remain in states of reduced activity until opportunity returns. This is also where the conversation becomes useful for understanding what appears not to belong. Because when people first encounter a report of microbes in boiling springs, under Antarctic ice, deep in basalt, inside rocks, around hydrothermal vents, or in hypersaline pools, it can feel as though the organism and the setting are mismatched. Life seems to have turned up in the wrong room. But that reaction often reflects the fact that our working definition of a suitable room was too narrow. There is a good scientific reason to be careful here, because not every claim of extreme life holds up equally well. Some reports are complicated by contamination. Some involve dormant survival rather than active growth. Some environments are heterogeneous, with tiny microhabitats more hospitable than the surroundings suggest. Some experimental results are difficult to reproduce, and the upper temperature or salinity or pressure limits for active metabolism are not infinitely stretchable. There are real boundaries, and researchers spend a good deal of effort trying to define them properly. That caution matters, otherwise every unusual environment becomes a stage for exaggeration. But even after applying careful standards, the range remains astonishing. Life on Earth occupies acidic rivers, alkaline lakes, deep marine sediments, radioactive settings, glacial ice, hydrothermal systems, hypersaline basins, subterranean rock fractures, and the surfaces and interiors of minerals in places where older biology would barely have thought to look. These are not all edge cases in the sense of rare curiosities. Some represent substantial, stable communities with long evolutionary histories. They are part of the normal planet once you stop defining normal solely by human comfort. That last distinction matters more than it might seem. Much of our intuition about habitability is quietly anthropocentric. We notice environments that feel livable to us, or to large animals and plants we recognize. We build a kind of emotional zoning map. Forest, yes. Meadow, yes. Seafloor vent field at crushing pressure with sulfur-rich fluids and no sunlight, absolutely not. But microbes do not care about our emotional zoning map. They care about gradients, molecules, energy sources, repair mechanisms, and whether evolution has had enough time to produce a workable solution. In fact, some of the most productive scientific questions come from separating habitability from familiarity. An environment may be deeply unfamiliar and still chemically suitable for some form of life. Conversely, an environment may look physically gentle and be metabolically poor. It is not the scenery that matters, it is the constraints and opportunities at the cellular level. Once scientists began following that logic more consistently, Earth started looking less like a planet, with a few isolated habitable patches, and more like a planet with a vast range of biochemical neighbourhoods, some obvious, some hidden, some severe, but many more populated than expected. There is also something useful in the humility these discoveries enforce. We are often tempted to treat life as fragile because our own bodies are, and in a certain immediate sense that is true. Most complex surface organisms are limited by fairly narrow conditions, but life as a planetary phenomenon is tougher, more adaptable and more inventive than our own comfort range suggests. It does not survive everywhere, it does not solve every chemical problem, yet it repeatedly finds a way into settings that look, from the outside, like the end of the story. Sometimes the real surprise is not that life is present, but that it has been there for so long without our noticing. Entire metabolic strategies remained hidden because we had not sampled the right place or asked the right question. Organisms were cycling sulfur, iron, methane, hydrogen, and other compounds in the dark, while the surface world went on assuming the planet's main biological action was happening where the sunlight fell, which in fairness is where a great deal of visible life is. But visible life is not the whole accounting. The implications of all this stretch beyond curiosity. It changes how we think about global cycles of carbon, sulfur, nitrogen, and metals. It changes how we model the limits of ecosystems, the resilience of microbes, the origins of life, and the possibility of life in seemingly hostile environments elsewhere. But even if we stay firmly on Earth, the lesson is already substantial enough. The planet contains habitats that look chemically or physically unreasonable to us, and yet support living systems that are entirely native, entirely natural, and entirely real. So when we say life where life should fail, what we really mean is life found beyond the boundary drawn by older assumptions. Not miraculous life, not misplaced life, not biology breaking the rules, biology revealing that the rules were drawn too tightly, perhaps by observers who had spent too much time imagining life from the perspective of parks, gardens, and moderately successful camping trips. And once that boundary starts to move, it becomes harder to maintain confidence in our first impressions of what belongs and what does not. If life can inhabit the deep crust, acidic pools, boiling vents, frozen brines, and salt-saturated waters, then the next surprise is not that organisms survive in difficult places. The next surprise is often the organisms themselves, the specific creatures and microbial communities that emerge from Earth's least likely corners, looking as though they were designed to make our old categories feel slightly embarrassed. And that is where the picture becomes even more difficult to keep tidy, because once we stop arguing about whether life can exist in harsh places at all, we have to face the organisms that actually do the existing. This is often the point where the planet becomes less like a reassuring biology textbook and more like a very old cabinet full of specimens collected by someone with a mischievous sense of order. The settings are strange enough. The creatures themselves do not always help. Some look improvised, some look ancient, some behave in ways that seem almost offensively practical, as though evolution, when faced with impossible conditions, simply rolled up its sleeves and began making adjustments, without worrying too much about elegance. One of the reasons these organisms feel so out of place is that our image of life tends to be built around familiar scale and familiar shape. We're comfortable with birds, fish, trees, mammals, insects, flowers, even with the occasional fungus that looks as though it has had strong opinions about damp weather. But a great deal of Earth's most surprising life does not announce itself in forms that suit our instincts. It appears as microbial mats clinging to mineral surfaces, as pale crustaceans in underwater caves, as worms without mouths or guts, as shrimp gathering around chemical vents in complete darkness, as tiny animals surviving dehydration, radiation, freezing, and vacuum-like conditions with a calm that borders on insulting. These are not creatures that seem designed to reassure us that nature follows the expected menu. The deeper truth is that Earth's unlikely corners do not merely host life in general, they host organisms shaped specifically by those corners. The environment is not a backdrop. It is an editor. It removes what does not work, rewards what does, and repeats this process over spans of time so long that the final organism can look less like a compromise and more like a declaration. Darkness selects. Pressure selects. Heat selects. Salinity selects. Isolation selects. Toxic chemistry selects. And once enough selecting has occurred, you end up with creatures that seem almost too specifically fitted to their circumstances to belong anywhere else. Perhaps one of the most famous examples is the giant tube worm Riftia pachyptilla, found near hydrothermal vent systems. If you had to invent an organism to unsettle someone's neat understanding of animal life, this would be a strong candidate. It is a large red-plumed worm that lives in a tube, entirely without a digestive system in the normal sense. No mouth, no stomach, no intestines. That sounds to the average vertebrate like a rather serious oversight. Yet Riftia thrives because it houses internal symbiotic bacteria that oxidize hydrogen sulfide and use that chemical energy to produce organic compounds. The worm supplies the bacteria with the ingredients they need, including sulfide, oxygen, and carbon dioxide, and the bacteria in turn effectively feed the host. It is not an animal surviving despite the absence of sunlight and conventional food. It is an animal built around a partnership that makes the chemistry of the vent system directly useful. There is something very clarifying about that. It reminds us that when conditions become extreme, life does not always survive by doing more of the same. Sometimes it survives by reorganizing the relationship between organism and environment so completely that the end result looks almost like a new category of ordinary. Riftia does not seem bizarre because life has gone wrong. It seems bizarre because we are used to animals living in ecosystems ultimately powered by sunlight. Remove that assumption, and the worm begins to look not absurd but perfectly logical. Hydrothermal vent shrimp offer a similar correction. Species such as Rimicaris exoculata gather in dense numbers around vent chimneys on the mid-Atlantic ridge, clustering in hot, dark, chemically active water that again seems less like a habitat than a test of what the word habitat can be persuaded to mean. These shrimp possess unusual structures associated with light detection and carry symbiotic bacteria. The details of how they orient, where they cluster relative to vent flow, how they manage temperature gradients, and how their symbioses function have all added to the sense that deep-sea vent organisms are not merely surviving the vent environment. They're using it with a precision that surface intuition does not prepare us for. Then there are the Pompeii worms, animals so often mentioned in extreme environment discussions that one begins to suspect they rather enjoy the publicity. Alvinella pompahana lives on the walls of hydrothermal vent chimneys, with parts of its body exposed to temperatures that would be intolerable for most known animals, while the cooler surrounding seawater provides some relief. There has been debate and refinement over exactly how high the temperatures are in the worm's immediate living conditions, because vent environments are sharply variable over very small distances, and sensational claims are easy to overstate. But even with careful handling of the evidence, these worms remain among the most heat-tolerant animals known. Their backs are coated with symbiotic bacteria, which adds yet another layer of peculiarity to an animal already living in conditions that sound less like zoology and more like a heating system failure. The deep sea also gives us organisms that make darkness feel less like an absence and more like a design principle. The so-called yeti crab, Kiwa hirsuta, and its relatives, found near hydrothermal vents and cold seeps, are covered in hair like setae on their claws and limbs that can host bacteria. The visual impression is unusual enough that the creature sounds fictional at first, like something a child might describe after being told one too many stories about monsters near the seabed. Yet there it is, entirely real, adapted to a world where symbiosis, chemical energy, and sensory strategies differ markedly from the brightly lit ecological dramas we tend to imagine when we hear the word animal. Cold seeps produce their own set of odd residents, among them clams, mussels, and tube worms that depend on microbial partners using methane or sulfide. Once again, the broader lesson is that creatures from unlikely corners are often inseparable from equally unlikely chemistry. They are not isolated marvels. They are the visible part of deeper systems where water, rock, gas, and microbes create an energetic basis for whole communities. A clam at a methane seep is not just a clam in an unusual place. It is part of a local bargain between geology and biology. Caves, especially underwater caves, have a habit of producing animals that feel as though they have been edited by darkness. Fish lose pigment and eyes. Crustaceans become pale and elongated. Sensory structures shift. Metabolism changes. Reproduction adapts to sparse resources. In many cases, these are not recent improvisations, but the outcomes of long isolation. Cave fish are a particularly good example because they invite the question of loss rather than gain. We often imagine evolution as an accumulation of features, but in stable darkness, eyes can become costly, unnecessary, or vulnerable. Pigment becomes pointless. Natural selection and drift can then reshape the animal accordingly. The result is something that appears incomplete to us, only because we are comparing it to surface relatives shaped by light. That is a common mistake in how we think about extreme or isolated organisms. We interpret them from the perspective of what is missing rather than from the perspective of what works. A blind cave fish is not a damaged fish. It is a fish for which vision has ceased to be worth the developmental investment. A pale crustacean in a cave is not unfinished. It is simply not paying for colour it cannot use. In this sense, creatures from Earth's unlikely corners are often only unlikely from the outside. From within their environment, they make excellent sense. Subglacial lakes and permanently cold environments reveal another version of this logic. Beneath Antarctic ice, and within sea ice, communities live microbes and small organisms adapted to cold, darkness, and limited nutrient flow. The challenge here is not just avoiding freezing, though that is certainly high on the list. It is maintaining cellular function when chemistry slows, membranes stiffen, and liquid water exists only in restricted forms. Some organisms produce antifreeze proteins or other protective compounds. Others exploit tiny brine channels or seasonal opportunities. The striking thing is not that one or two cells persist accidentally. It is that whole communities organize themselves around constraints that would once have been treated as biologically terminal. And then there are the animals that survive not by permanent metabolic activity in impossible conditions, but by entering states that make survival itself look almost suspended. Tardigrades are the celebrities of this category, and with some justification, though their fame occasionally encourages people to speak of them as though they are indestructible space pixies. They're not magical. They are microscopic animals with very impressive physiological strategies. In active life, they inhabit mosses, soils, sediments, freshwater films, and a range of other damp environments. But when conditions deteriorate, some species can enter a desiccated ton state in which metabolism becomes extremely reduced. In that state, they tolerate dehydration, freezing, low pressure, high pressure, radiation, and other stresses far beyond the range of ordinary animal resilience. What makes tardigrades so compelling is not that they are breaking the laws of biology. It is that they reveal just how effectively a small body can be stabilized when evolution has had reason to solve the right problems. Protective molecules, vitrification-like states, repair mechanisms, structural resilience, all of these contribute. They are not strolling cheerfully across the vacuum of space in full metabolic operation, but as examples of how Earth life can endure conditions that seem entirely unreasonable for animals, they are difficult to ignore. They feel as though they belong in a speculative story and yet are quite content living in your gutter moss. Rotifers, nematodes and brine shrimp cysts offer their own versions of extreme endurance. Some can survive drying, freezing or long dormancy, returning to activity when conditions improve. Again, the lesson is not that life is always active everywhere. It is that persistence can take forms more varied than ordinary observation suggests. Survival does not always mean business as usual. Sometimes it means waiting brilliantly. Hypersaline environments host creatures and communities that feel equally improbable. Brine pools on the seafloor are among the strangest habitats on Earth. These are dense, salty bodies of water sitting on the seabed like underwater lakes, sometimes bordered by sharp boundaries where chemistry changes abruptly over small distances. Oxygen may be low or absent, sulfide may be abundant. Salinity can be several times that of ordinary seawater, yet microbes flourish there, and in some cases multicellular organisms occupy the fringes or exploit associated sediments. Even when the central brine itself is too harsh for most complex life, the surrounding gradients create niches. The edge of the unlivable turns out to be surprisingly busy. On land, soda lakes and salt flats present similar combinations of chemical hostility and biological creativity. Brine flies, specialized microbes, algae, and archaea can dominate these systems. The colors alone often make them seem unreal. Lakes turn pink, green, orange or crimson under the influence of pigments produced by organisms coping with intense sunlight, salinity, and other stressors. We are tempted to treat such places as exceptions, but Earth contains a remarkable number of them. They are not biologically empty mistakes in the landscape, they are selective arenas. Another category of unlikely creature comes from environments saturated with toxic substances or heavy metals. In regions contaminated naturally or by mining activity, microbial communities can evolve tolerances to arsenic, mercury, copper, uranium, and other compounds that would be disastrous for most life. Some microbes do more than tolerate them. They use redox transformations involving these elements as part of their metabolism. To us, A metal-laced, acidic, toxic drainage stream looks like an ecological warning label. To the right microbe, it is a livelihood. This matters because it reminds us that poisonous is often organism-specific and context-dependent. The same chemistry that excludes one form of life may support another. There are even organisms associated with radioactive environments that continue to force revisions of what we think biological damage ought to prevent. Certain fungi have been found in highly radioactive settings, including areas around Chernobyl, and have prompted discussion about how melanized organisms may tolerate or exploit such conditions. It is easy to exaggerate these cases into headlines about radiation-eating life forms with theatrical ambitions. The reality is more careful and more interesting. Ionizing radiation is dangerous. Cellular damage is real. But some organisms possess repair systems, protective structures, or metabolic strategies that allow them to persist where other life would struggle. Once again, a habitat we instinctively classify as no place for normal biology turns out not to be empty. The deep subsurface brings its own cast of improbable residents. Here the creatures are less likely to charm the imagination visually, and more likely to challenge it conceptually. Bacteria and archaea living kilometres below the surface, in fractured rock, isolated water, and energy-poor conditions, often persist at rates so slow that our ordinary ideas of ecology begin to wobble. Some divide only rarely, some repair damage and maintain viability across extraordinary spans of time. Some depend on hydrogen produced by water-rock interactions or on geochemical reactions involving sulfur and iron. In such places, life is not exuberant in the manner of a rainforest. It is patient. It exists under tight budgets, making a living in ways that seem almost too sparse to count until measurement proves otherwise. And then, scattered through all of this, are the creatures whose oddity comes not solely from chemistry or temperature or pressure, but from isolation so long and complete that they seem like leftovers from different eras of the planet. Deep cave amphipods, ancient lineages in subterranean aquifers, isolated fish, crustaceans and invertebrates on islands, in lakes, or in relict habitats, all contribute to the feeling that Earth has compartments. Places where evolutionary experiments can continue mostly out of sight, producing organisms that look unfamiliar not because they are from elsewhere, but because we have not spent much time visiting their kind of world. This is one of the subtler meanings of "doesn't belong here." Sometimes the organism seems out of place, not because the environment is chemically outrageous, but because it feels like a survivor from the wrong map. A crustacean from a dark-cast aquifer may seem disconnected from the surface life around it. A fish in a cave may appear to have stepped out of an unfinished design plan. A worm living on a vent chimney may look as though it belongs to a planet we have not visited yet, but all of them belong exactly where they are, shaped by the corner of Earth that made them. The more we learn about these organisms, the less convincing the old boundary between ordinary and extraordinary becomes. Creatures from unlikely corners are not a separate category of life standing apart from the rest. They are life doing what life has always done, finding gradients, exploiting opportunities, partnering with microbes, reducing costs, increasing tolerances, losing features that no longer matter, and surviving in niches that become visible to us only after technology and curiosity catch up. That does not mean every dramatic-looking creature is profound in the same way. Some are simply unfamiliar, some are biologically interesting but not conceptually disruptive. It is easy to overstate the weirdness of anything pale, deep sea, or covered in bacteria, and people have been doing exactly that for years with great enthusiasm. But even after the exaggeration is stripped away, enough remains to justify the sense of surprise. Earth produces animals and microbial communities in places and forms that repeatedly expose how narrow our first guesses about habitability and adaptation have been. There is something almost comforting in that, though perhaps not if you are trying to keep the natural world neatly categorized before sleep. It suggests that the planet is not stingy with possibility, given enough time, enough isolation, enough selective pressure, enough chemistry, enough darkness, enough salt, enough pressure, enough cold or heat. It will fill available niches with organisms that make use of them. Some will be tiny, some will be conspicuous, some will look ordinary until you learn how they live. Others will look impossible until you realize the impossible part was merely your assumption. And once you have accepted that Earth can produce creatures that seem entirely mismatched with the settings we once thought lifeless, it becomes easier to see why the same sense of dislocation appears in another domain as well. Not just in living things, but in objects made or shaped by human hands, or at least apparently so, that turn up in the wrong layer, the wrong rock, or the wrong story, leaving behind that same quiet feeling that something has arrived before its explanation. That feeling of misplacement becomes especially powerful when the thing we are looking at appears to have been made, shaped, or engineered by human hands, because then the question changes slightly. A strange creature in a deep-sea vent asks how life adapted. A strange object in the wrong historical setting asks who made it, when, and with what knowledge. And human beings are much less calm about those questions. The moment an artifact seems older than it should be, more complex than expected, or embedded in a context that does not match the usual timeline, the imagination starts stretching itself before anyone has even finished brushing off the dirt. There is a very reliable reason for that. Objects feel deliberate. A stone may be unusual by accident, chemistry, or pressure. A creature may be strange through evolution. But an object that looks made carries intention with it. It implies a mind, a culture, a set of tools, a level of skill, and a place in a sequence of development. If that sequence seems wrong, then the object does not simply challenge one geological explanation. It unsettles our sense of history. And history, unlike a mineral phase, comes with people attached to it, which means it also comes with pride, storytelling, national identity, favourite theories, alarming documentaries, and at least one person every decade insisting that mainstream archaeology is hiding something under a tarp. The phrase objects that arrive too early is therefore best understood as a shorthand for a certain kind of tension. It does not mean the object literally travelled through time, though I appreciate that such a solution would at least be memorable. It means that according to our existing models of technology, chronology, or cultural development, the object seems ahead of schedule. It appears to require methods, designs, or contexts not usually associated with its date. Sometimes that impression survives careful study and forces a real revision. Sometimes it fades once better dating, better context, or a less enthusiastic interpretation arrives. And sometimes the object itself is perfectly ordinary while the story attached to it has wandered off into the hills. This is why context matters more here than almost anywhere else. An artifact on its own can be suggestive. An artifact in a well-documented layer, with associated material, secure dating, manufacturing traces, and a clear archaeological setting becomes far more useful. Remove the context, and almost anything can be made to sound mysterious. A corroded lump becomes a lost battery. A natural concretion becomes a machine part. A decorative object becomes evidence of impossible precision. A later intrusion into older sediment becomes a headline about ancient civilizations in the wrong rock. Human beings are remarkably good at extracting wonder from incomplete information. Science is then left with the slower job of sorting out which part of the wonder can stay. One of the finest examples of an object that once seemed almost absurdly advanced, but turned out not to be impossible at all, is the Antikythera mechanism. Found in a shipwreck off the Greek island of Antikythera, this device, dating to around the 2nd or 1st century BCE, is a geared instrument of astonishing complexity used to model astronomical cycles. The first time people understood what it really was, the response was entirely reasonable. Surely not. Surely this degree of mechanical sophistication, this interlocking gearwork, this compact predictive design, belonged much later in technological history. It seemed to arrive centuries too early, and yet it was real, ancient, and entirely of this world. The mechanism did not prove a lost global super-civilization with suspiciously polished sandals. It proved something both more modest and more interesting. It showed that Hellenistic craftsmanship, mathematics and astronomy had reached a level of mechanical expression far beyond what many had assumed. It also hinted that the surviving record was incomplete. Perhaps such devices were rare. Perhaps they were once more numerous and mostly lost because bronze has a habit of being melted down when later generations need bronze for other things. Perhaps the tradition continued in forms we only partly glimpse. The point is that the Antikythera mechanism did not sit outside history, it expanded it. That is often the healthiest outcome in cases like these. The object does not overturn everything. It sharpens what we know, reveals a gap in preservation, and reminds us that the surviving material record is not a complete inventory of all human skill. Entire technologies can appear to begin abruptly simply because earlier examples did not survive. Wood rots, textiles vanish, iron corrodes, workshops are destroyed, libraries burn, shipwrecks sink. A technological tradition may leave behind only fragments, or one highly inconvenient masterpiece resting underwater for 2,000 years. The Antikythera mechanism is therefore a useful antidote to both extremes. It prevents us from dismissing every difficult object as impossible, and it prevents us from assuming that any advanced-looking artifact must belong to a civilization far beyond the one in which it was found. Sometimes the timeline is wrong only in the sense that our version of it was too simplified. A more controversial case is the so-called Baghdad battery, a group of small clay jars containing copper cylinders and iron rods, discovered near Baghdad and often dated to the Parthian or Sasanian period. These objects became famous because someone suggested they might have functioned as galvanic cells if filled with an acidic liquid. This immediately gave the public exactly what it likes most, an ancient object that can be described in modern technological language. Suddenly the past had electricity, and everyone became very animated. The problem is that the evidence is ambiguous. Could such a jar generate a small electrical potential under the right conditions? Yes, in principle. Does that mean it was definitely used as a battery? No. The archaeological context is incomplete, the function is uncertain, and alternative explanations remain plausible. It may have been a storage vessel, a container for scrolls, or something else entirely. The jar is real. The object is old. The leap from possibly capable of electrochemical behaviour to ancient electrical device is where things become less secure. And that too is instructive, because many objects that seem too early live in this middle zone. They are not frauds, they are not imaginary, they simply carry more interpretation than evidence. A suggestive physical form is asked to support a very large claim. Sometimes it can, often it cannot. Archaeology, like geology, is full of items that look far more dramatic before the paperwork arrives. Then there are the examples that appear impossible mainly because the context has been misunderstood. The so-called London hammer is perhaps one of the better-known cases in popular anomaly culture. The story usually goes that a hammer was found embedded in ancient rock, implying a human-made object in a geological layer millions of years old. This is very exciting if one's favourite hobby is overthrowing chronology before lunch, but the key issue is that the hammer was not proven to be as old as the host material was claimed to be. It appears to have become enclosed in a concretion, a hardened mineral mass that can form around objects over much shorter timescales than the surrounding geological formations themselves. In other words, it is not an industrial tool from the age of dinosaurs. It is a cautionary tale about what happens when people mistake a secondary enclosure for original deposition. Concretions are excellent at creating this sort of confusion because they look ancient and authoritative. Put an ordinary object inside a hard mineral shell, and suddenly it appears to have emerged from the deep past wearing a geological disguise. Nature is very good at this kind of accidental theatre. The shell feels older than the object. The eye believes the shell. Then chronology gets dragged into an argument it did not ask for. The same applies to a range of alleged impossible artifacts found in coal seams or ancient strata. In many cases, the reports are poorly documented, repeated second-hand, or stripped of the details needed to evaluate them. In others, later intrusion, contamination, mistaken identification, or outright storytelling plays a role. Coal mines and quarries have long histories of producing rumours because they expose deep materials in industrial settings where documentation is not always pristine. A shaped lump, an odd mark, or a corroded tool can quickly acquire a tale of impossible antiquity if no one is around to insist on boring but useful questions like, where exactly was it found? Who recorded it? Was the layer disturbed? And does anyone have the object now? That last question is often devastating to mystery. Where is it? Has ended many grand theories. Quite a few objects that allegedly arrived too early survive mainly in anecdote, newspaper clippings, or descriptions written long after the event. Without the object, the exact provenance or reliable records, all that remains is the pleasure of speculation. Which is not nothing, but it is not evidence either. Still, it would be a mistake to imagine that every early-looking object dissolves under scrutiny. Some really do reveal levels of skill that force a revision of older assumptions, just not usually in the sensational way people hope. Ancient metallurgy is a good example. The iron pillar of Delhi, for instance, has long attracted attention because of its resistance to corrosion. For a casual observer, an ancient iron structure surviving so well can feel suspiciously advanced, as though someone had acquired metallurgical knowledge before the rest of history had read the manual. In reality, the pillar reflects sophisticated ironworking and a particular composition and environmental history that promoted a protective passive film. It is not impossible. It is impressive, and impressive is often enough. The same is true of certain ancient glasses, pigments, concrete formulations, stoneworking techniques, and alloy behaviours that once looked nearly irreproducible. Roman concrete, for example, has become something of a modern obsession because some marine structures lasted for extraordinary lengths of time. That does not mean Romans possess secret industrial sorcery. It means their materials, ingredients, environmental interactions, and construction goals differed in important ways from many modern formulations. Once studied carefully, the apparent mystery becomes a more detailed technical question. Why did this recipe endure? What mineral phases formed? How did seawater interaction help rather than harm? A material that seems too good for its age turns out to be less an anachronism than a reminder that progress is not always linear in the simplest sense. Knowledge can be gained, lost, fragmented, and rediscovered. This is one of the most useful correctives in thinking about early objects. We often imagine technological history as a smooth staircase. One step, then the next, then the next. Bronze, then iron. Simple gears, then better gears. Crude construction, then improved construction. Reality is much messier. Skill can peak locally. Craftsmen can solve problems with extraordinary precision in one domain while lacking tools in another. A society can build monumental stonework without modern steel. Another can develop advanced astronomical calculation devices without industrial manufacturing. Knowledge can exist in islands. It can fail to spread. It can be forgotten. It can survive only in one wreck, one inscription, one ruined workshop, one object at the bottom of the sea. That is why too early is often not a sign that history is broken, but that our picture of developmental pacing has been smoothed too much. Real cultures do not evolve in neat bullet points. They improvise, they specialise, they lose things, they achieve odd brilliance in particular corners. If our timeline says an object should not exist yet, the first response should not be panic. It should be curiosity about what hidden tradition, local expertise, or preservation gap the object may be pointing toward. There are also cases where natural objects are mistaken for artifacts, and thereby seem to arrive too early, simply because they were never manufactured in the first place. The Klerksdorp spheres from South Africa are a good example of how geology and imagination can become badly entangled. These small rounded objects, some with grooves, have been described in sensational accounts as ancient manufactured spheres found in very old rock. In reality, they are understood as naturally formed mineral concretions or pyrophyllite-associated structures, not crafted technological artifacts from a vanished civilization with a strong preference for small balls. Yet the visual impression, combined with age claims, was enough to propel them into the mythology of impossible objects. A groove, after all, does not care whether it was made by a machine or a mineral process. It simply sits there and lets people argue over it. That may sound slightly unfair to the enthusiasts, but the distinction really matters. Human pattern recognition is useful right up until it becomes overconfident. We are excellent at seeing design, intention, and familiarity in shapes, textures, and symmetries. Archaeology depends on this skill. So does mistaken archaeology. A regular pattern may signal craftsmanship, or it may signal crystal growth, fracture, erosion, concretion, biological boring, or sedimentary sorting. Nature can produce things that look planned. Humans can produce things that look rough and natural. The border is not always obvious from appearance alone. One reason these objects grip the imagination so strongly is that they seem to promise a shortcut to hidden history. If one impossible tool were genuinely found in a secure geological layer, tens of millions of years too old, the implications would be extraordinary. So people keep looking, retelling, and hoping, and sometimes that hope outruns the evidence by a very great distance. Yet underneath the exaggeration there remains a legitimate and interesting question. How incomplete is our material record of the past? The answer inevitably is very incomplete. That does not license any claim we fancy. But it does mean genuine surprises are always possible. Archaeologists and historians know this very well. New finds regularly push technologies earlier, change regional chronologies, or reveal wider trade networks than expected. Ancient beads appear farther from their source than assumed. Metallurgical practices turn up earlier in one culture than in another. Symbolic objects, textiles, pigments, and sophisticated tools emerge from contexts that require a careful redrawing of timelines. Most of these revisions are not dramatic enough to become household mysteries, but they matter. The past is continually being adjusted, not because all chronology is unreliable, but because new evidence keeps filling in blank sections. This is, in a way, the most scientifically satisfying version of the too early problem. Not impossible artifacts, but underestimated histories. A technology was present earlier than documented. A method appeared in a region thought to have adopted it later. A device reflects a craft tradition we only partly understand. An object survives as a lone witness to a broader, mostly vanished competence. That does not make the past supernatural. It makes it patchy. And patchiness is probably the great hidden theme of all these cases. We do not possess the ancient world in full. We possess survivals. We work from fragments, biases of preservation, chance recovery, and the accidents of excavation. Organic materials disappear. Metal is recycled. Sites are built over. Sediments shift. Looting removes context. Fires destroy archives. Entire stretches of ordinary human work vanish. Against that background, it should not surprise us that now and then an object appears to leap ahead of the record. The record is full of holes. What matters is how we respond. There are really two temptations to avoid. The first is the sensational one. Every puzzling artifact becomes evidence of hidden civilizations, impossible antiquity, or some vast conspiracy of denial. The second is the dismissive one. Every uncomfortable find must be a mistake because our existing timeline feels too settled to disturb. Neither approach is especially useful. Better to keep the object in view, guard the context, ask careful technical questions, and accept that some finds will become less mysterious, while others will quietly change the story. That slower approach is less exciting at first, but it has a much better track record. It gave us the real significance of the Antikythera mechanism, instead of a fantasy about time travellers dropping tools overboard. It gives us better metallurgy instead of magical iron. It gives us more precise chronology instead of theatrical collapse. It also protects us from being fooled by concretions, mineral oddities, and artifacts whose mystery lies mainly in the way they were reported rather than in the thing itself. So when objects appear to arrive too early, they are not all pointing in the same direction. Some are misunderstandings, some are natural lookalikes, some are genuine technical achievements emerging from underestimated contexts. Some are reminders that preservation is poor and history unevenly sampled. And a few remain tantalizing because the evidence is real, the craftsmanship is undeniable, and the gap between object and expectation persists just long enough to make us re-examine the assumptions doing the judging. Which brings us rather naturally to another category of things that seem to show up before we are ready for them. Not as solid artifacts this time, but as repeated forms and signals that hint at order where we expected noise, as though the planet and sometimes the people on it had been leaving patterns in plain sight long before we fully learned how to read them. The trouble with patterns is that we are built to see them even when they are not there, and also to miss them when they are. Human perception is wonderfully unreliable in that very specific way. Give us 3 dots and a line, and we will begin suspecting intention. Give us 1,000 measurements scattered across years, sediments, seafloor readings, animal movements, atmospheric pulses, or desert vegetation, and we may call it noise simply because it does not arrange itself politely enough for the eye. This makes patterns one of the strangest kinds of discovery on Earth, because they rarely arrive as a single object you can hold in your hand. They emerge slowly. They show up in repetition, in spacing, in rhythm, in correlations between things that were not originally expected to be connected. A lone anomaly can be dismissed as error, accident, contamination, or one very overexcited graduate student. A pattern is harder to get rid of. Once it appears often enough, in enough places, under enough scrutiny, it begins pressing on the edge of whatever theory was supposed to contain it. That is one of the reasons patterns hidden in noise can feel so unsettling. They do not merely say that one thing is strange. They suggest that the system itself has structure we fail to notice. And when that system is the Earth, the implications can be rather large. A repeated stripe on the seafloor is not just a stripe. A persistent vibration under the background clutter is not just a hum. A regular spacing between patches of vegetation in an arid landscape is not just a visual curiosity. It is a clue that some process is organizing matter, energy, stress, growth, chemistry, or motion in a way we did not fully appreciate. There is also something psychologically difficult about patterns, because they force us to live in an uncomfortable middle ground. Too much skepticism, and we dismiss the real thing. Too little, and we start seeing messages in every hill, every signal, every oddly shaped puddle, and every coincidence that survives long enough to acquire a reputation. Science spends a great deal of time trying to navigate that middle ground. It asks whether the apparent pattern is statistically robust, repeatable, physically plausible, and independent of the methods used to detect it. This is less glamorous than immediately announcing that the Earth is sending us coded warnings, but it has a much better success rate. Sometimes the pattern turns out to be one of the most important discoveries in the history of science. The magnetic stripes on the ocean floor are a beautiful example of that. Before they were understood, the seafloor was not exactly thought to be simple, but its broader organisation was far from clear. Then marine geophysics began revealing alternating bands of normal and reversed magnetic polarity, preserved in the basalt of the oceanic crust, arranged symmetrically around mid-ocean ridges. At first, these data could have looked like a nuisance. Measurements vary, instruments drift. The ocean is not known for making fieldwork especially convenient, but the pattern held. Once recognised, it became one of the strongest lines of evidence for seafloor spreading and plate tectonics. The Earth had been recording the history of magnetic reversals in cooling crust, and leaving the record spread out like a barcode across the seabed. Not because it wanted to be helpful, naturally. but because physical processes sometimes preserve information whether we are ready for it or not. That is one of the most important things patterns teach us. The world is often legible before it is readable. The structure is there, the problem is us. A similar lesson appears in the continuous seismic hum of the Earth. Most people imagine earthquakes as discrete events. The ground is quiet, then suddenly not quiet, and everyone becomes very attentive to furniture. But the planet also vibrates continuously at low levels. There is a background signal, a kind of persistent trembling, much of it driven by the interaction of ocean waves, atmosphere, and the solid Earth. For a long time, a good deal of this background motion was treated simply as noise, the sort of thing one tries to remove in order to see the important signal more clearly. Then, as instruments improved and analysis became more refined, that noise itself became informative. It could be used to image subsurface structure, to monitor changes in volcanic systems, to study crustal properties, and to understand how energy moves through the planet. That shift is both technical and philosophical. Noise is not always absence of meaning. Sometimes it is the wrong level of meaning for the question you originally asked. You were listening for earthquakes and found ocean-generated vibration instead. You were trying to remove the clutter and accidentally discovered a new way to see through the crust. Earth is particularly good at this. It hides useful information in signals we first classify as interference. The same can be said of slow slip events and tectonic tremor, phenomena that only became clear once researchers learned to pay attention to subtler patterns of fault motion. Instead of major ruptures only, some plate boundaries also creep, pulse, and release energy in slower, quieter ways. To an older picture of tectonics, that could seem like the wrong kind of earthquake, as though the planet were moving off script. In reality, it was simply behaving with more variety than the simplified model had included. You can see the same tension in landscapes that arrange themselves with suspicious regularity. The fairy circles of arid regions, especially in Namibia and parts of Australia, are a good example. Seen from above, these landscapes contain near-circular bare patches ringed by vegetation, repeating across broad areas with spacing that looks too orderly to be accidental, and too organic to be obviously engineered. People naturally find them hypnotic. They look like the sort of thing that ought to have a neat explanation. This is where science becomes slightly impolite and says, "Not so fast." There have been multiple explanations proposed for fairy circles. Termite activity has been one. Self-organisation driven by water competition among plants has been another. In some regions, one mechanism may dominate. In others, a different combination of soil, climate, vegetation dynamics, and ecosystem engineering may matter more. That is part of what makes the circle so interesting. They're not merely odd shapes on the ground. They're repeated spatial solutions emerging from dry land systems under stress. The pattern itself is real. The full story behind all occurrences is more complicated. And this is precisely the kind of case that fits our larger theme so well. The circles look as though they should not belong there because the landscape seems to have arranged itself with an unnatural degree of order. But the order may be entirely natural, produced by feedbacks between plants, water, soil properties, and living communities interacting over time. Once you start noticing this, the Earth begins to look less random than before, though not in a tidy or comforting way. Periglacial landscapes, for instance, often produce sorted stone circles, polygons, and stripes through freeze-thaw processes. Stones migrate, finer sediments move differently, and repeated cycles of freezing and expansion gradually sort the ground into astonishingly regular forms. Seen in isolation, some of these features can look artificial, almost ceremonial, as though someone had taken considerable trouble to arrange rocks into careful shapes in extremely inconvenient weather. But again, the pattern emerges from process. Frost heave, soil movement, particle size, drainage, and repeated cycles of disturbance create order from local interactions. No planner required. The planet, given enough repetition, is quite capable of laying out a design all by itself. That may be one of the deepest reasons natural patterns feel so uncanny. They resemble intention while being produced without it. We are used to order meaning plan. A row of houses implies builders. A grid implies surveyors. A repeated symbolic motif implies culture. But the Earth generates regular spacing, branching networks, striped rock, concentric deposits, and periodic pulses through physics, chemistry, and biology alone. River systems branch because flow and topography demand it. Cracks form polygons because drying or cooling redistributes stress. Vegetation self-organizes because competition and resource flow have consequences across space. What looks like a message is often an equilibrium, or at least the nearest thing nature allows. Even so, there are cases where the pattern seems to arrive before the explanation is ready. One of the best examples is found in the study of atmospheric and electromagnetic signals. The Earth is constantly producing radio emissions, whistlers, crackles, pulses, and low-frequency phenomena associated with lightning, geomagnetic activity, auroras, and the movement of charged particles. If you convert some of these to audible sound or represent them visually, they can seem eerily artificial, almost as if some giant machine were operating just beyond the edge of perception. In reality, much of it is natural and increasingly well understood. But the broader lesson remains useful. A signal that sounds designed may simply be a consequence of physical systems interacting in ways our ears were never built to interpret directly. Ocean acoustics offers similar examples. The sea is full of sound, and not all of it is immediately identifiable. Ice cracking, undersea earthquakes, landslides, volcanic activity, waves, marine mammals, ship traffic, sediment movement, and thermal structure all contribute to a highly complicated acoustic environment. Every now and then a sound is recorded that seems too strange, too powerful, too oddly shaped to fit comfortably into existing categories. Often a sensible explanation eventually emerges. A dramatic oceanic sound once treated with some mystery may turn out to be ice-related, for instance, or the product of known but rarely recorded conditions. That does not make the episode uninteresting. Quite the opposite. It shows that the Earth system contains behaviours we only sometimes catch clearly enough to recognise. This brings us back to the problem of noise. Noise is often what we call a system before we understand what variables matter. Once the correct variables are found, the noise begins to separate into structures. Rhythms appear. Correlations sharpen. Features once treated as random become signatures of deeper processes. That transformation has happened over and over in climate science, geophysics, ecology, and geology. A set of isotopic fluctuations in sediment cores may initially look messy, then reveal repeating climatic cycles tied to orbital forcing. A scatter of volcanic tremor may begin to show patterns associated with magma movement. A confusing distribution of mineral traces across terrain may resolve into the footprint of buried ore systems. The Earth is not necessarily becoming more orderly in those moments. We are simply catching up. There is also a caution here, because pattern detection can become almost addictive. Once you begin finding meaningful order in surprising places, the temptation is to find it everywhere. This is how weak claims often enter the conversation. People see alignments, periodicities, numerical repetitions, geometric arrangements, or signal coincidences and rush to treat them as profound. Some are artifacts of sampling. Some arise from how the data were processed. Some are ordinary consequences of constrained systems. Some are genuine but trivial. Pattern alone is not enough. It must be tied to mechanism, or at least to a serious attempt at one. Otherwise, every patch of lichen and every odd echo becomes a revelation, and no one gets any sleep. Still, there are Earth patterns that remain productively unresolved, where the form is undeniable, but the governing process is still debated or only partly explained. Certain repeating landforms, some vegetation mosaics, some cave mineral growth patterns, some fracture networks, and some geochemical distributions fall into this category. Researchers can describe the regularity, they can model candidate mechanisms, they can compare environments, but the full accounting remains open. Those are often the most rewarding mysteries because they do not rely on fantasy. The pattern is real. The uncertainty lies in why this particular order emerged here and not somewhere else. Biology adds another layer to the story because living systems both generate and respond to pattern. Microbial mats form layered structures. Social insects create regular spacing in nests and mounds. Vegetation bands appear on slopes in semi-arid regions where water movement and plant growth feed back on one another. Forests show clustering and spacing shaped by competition, dispersal, disease, and disturbance. Coral growth, shell deposition, and stromatolitic layering all produce repeated forms that can look designed until one remembers that life is a very patient sculptor. Once organisms begin interacting with their environment in large numbers, pattern becomes almost unavoidable. This is one reason Earth can feel as though it is hiding messages in plain sight, not because there is a message in the theatrical sense, but because repeated structures across space and time imply underlying rules, and rules feel like intention when you first encounter them. A desert dotted with evenly spaced circles, a seafloor striped with magnetic memory, a landscape fractured into polygons, a cave lined with growth bands, a fault zone pulsing in slow rhythm, a background vibration carrying information about unseen rock layers. All of these prompt the same reaction. Something is organizing this. Something is writing shape into matter, and that reaction is not wrong, provided we keep the language grounded. The organizer may be stress, flow, competition, chemistry, freezing, magnetism, rotation, or repeated disturbance. The writing may be nothing more than process leaving a trace, but those traces matter. They turn the Earth from a pile of separate events into a system that records itself. You can see how powerful that becomes when a pattern is discovered only after someone stops looking at individual cases and starts looking at distribution. A single sinkhole is a nuisance. A mapped field of sinkholes revealing hidden karst structure is a geological story. One methane seep is an oddity. A repeating arrangement of seep sites along faults becomes a clue to deeper fluid migration. One unusual plant patch is local ecology. Hundreds of similarly spaced patches across a landscape become a signal that the environment is organising growth under scarcity. Pattern changes the scale of the question. This is also why some of the most interesting discoveries on Earth begin not with finding a new thing, but with realising that many old things belong together. Separate data points, once isolated, suddenly line up. The apparent clutter becomes family resemblance. A mineral anomaly here, a thermal anomaly there, a subtle elevation change, a geochemical trace, a seismic quirk, and before long the Earth starts giving away part of a buried structure or an active process it had managed to keep mostly out of sight. Hidden ore deposits are found this way. Volcanic hazards are tracked this way. Ancient climate cycles are reconstructed this way. So are many of the anomalies that first seem not to belong anywhere at all. If there is a quiet moral in all this, it may be that the Earth rarely wastes a process. If enough energy moves through a system for long enough, some signature usually remains. It may be faint. It may be disguised by later events. It may look like disorder until the right instrument or model is applied. But the record is often there, and once read, it can make the world seem both more lawful and more surprising at the same time. That combination is what makes hidden patterns so compelling. They do not simply solve mysteries, they often create better ones. Once you know the fairy circles are not random, you have to ask why that spacing. Once you know the seafloor stripes are real, you have to rethink continents. Once you know the Earth hum carries structure, you stop treating the quiet background as empty. Once you know slow tremor and subtle cycles exist, stillness itself becomes less straightforward. A stable landscape may be sorting itself. A silent fault may be moving. A barren plain may be negotiating water through geometry. And after a while, the distinction between signal and scenery starts to soften. The ground is not just there, it is expressing process. The noise was never merely noise, it was the part of the planet we had not yet learned to separate into readable form, which is a useful thought to carry forward, because some of the most striking examples of Earth seeming to write something down are not hidden in datasets at all, but spread across rock, soil and terrain in ways so visible they almost look deliberate, as if the planet had taken to leaving marks directly on the land. And in a sense it has. Not literally, of course. The Earth is not out there with a stylus, leaning over deserts and lake beds in the evening and drafting quiet little notes for the future. That would make field geology much more conversational, though perhaps also much less relaxing. But there are places where the ground does seem to behave like a recording surface. Marks appear across it, shapes repeat, lines stretch for kilometres, circles, spirals, ridges, trenches, scars and colour boundaries remain visible long after the events that formed them have passed. Some are made by people, some by water, wind, ice, fire, chemistry or impact. Some are combinations of all of those. And what gives them such power is that they seem to stand somewhere between language and landscape. They look as though they mean something before we fully know what that something is. That is why messages written in the ground can feel so strange. A rock is one thing. A metal deposit is another. Even a repeated pattern can remain abstract until you map it. But a visible mark on the land, especially a large one, carries an almost immediate sense of intention. We are primed for it. A line suggests direction. A circle suggests boundary. A repeated motif suggests design. A sudden contrast in colour or texture suggests that something happened here and happened clearly enough to leave a sign. Once that instinct is activated, the terrain begins to feel less like scenery and more like evidence. Sometimes that evidence really is human. The Nazca lines in Peru are probably the most famous example. Great geoglyphs scratched into the desert surface, depicting lines, trapezoids, spirals and animal forms so large they only fully resolve from above. It is difficult to look at them and not feel the immediate pull of the phrase written in the ground. They are deliberate, visible, ancient and large enough to invite all kinds of theories, from the reasonable to the deeply overcommitted. Yet what makes them truly interesting is not that they are inexplicable. They are not. They are the products of human labour in a dry environment where disturbance to the dark surface stones reveals lighter material beneath, and where minimal rainfall has helped preserve the resulting designs. Their exact social, ceremonial or practical meanings remain debated in parts, but the basic fact is clear. People mark the landscape in ways that outlasted them. That matters because it reminds us that the ground is a medium, not just a foundation. Humans have used it to encode roots, rituals, territory, memory, cosmology and power. Earthworks, burial mounds, ditches, ancient field systems, processional ways, hill figures, stone circles, and geoglyphs all belong to this wider category. They are places where the surface itself has been reorganised to hold information or significance. The White Horse at Uffington, for instance, cut into the chalk hills of southern England, is not just an image. It is a long-lived intervention in the land, maintained across generations. Desert kites in the Middle East, visible from above as large converging structures used for hunting, are not writing in the usual sense, but they are lines imposed on space with clear purpose. The Earth becomes plan, tool and memory all at once, and yet the sensation that the ground is carrying messages is not limited to human-made forms. Nature does this too, though less straightforwardly and with no obligation to use symbols we find convenient. Layered rocks are perhaps the most obvious case. To a geologist, a sedimentary sequence is already a kind of text. Grain size changes, fossils appear and vanish, colours shift, ash layers interrupt quieter deposition. Ripple marks, mud cracks, burrows, raindrop impressions and cross-bedding all record past environments in a way that can be read if one knows what to look for. A sandstone does not declare, Here was a river channel migrating across a floodplain under fluctuating flow conditions, but it may as well. The structures are there, the story is there, the message is not poetic, but it is legible. This is one reason Earth can seem to contain things that do not belong. When the ground preserves a signal from an environment utterly unlike the present one, the effect is dislocating. A desert reveals marine fossils. A mountain range preserves seafloor sediments. A glacial landscape sits over traces of ancient tropical life. The message written in the rock says, in essence, this place was not always this place. It had other climates, other coastlines, other chemistries, other inhabitants, and at times other positions on the planet entirely. Continents moved, seas advanced and retreated, ice came and went. The ground holds all of this without much concern for whether the transitions are easy for us to picture. There are individual layers that function almost like planetary headlines. The clay-rich boundary marking the end Cretaceous impact event is one of them. A relatively thin layer enriched in iridium, associated with shocked minerals and global disruption, appears in rocks around the world and records a moment when something enormous struck the planet and permanently altered the history of life. If one were inclined to dramatize, it would be tempting to say the Earth left us a line in the sediment reading, "Something terrible happened here," which on the whole would not be a bad summary. But the real power lies in the fact that a global event could be preserved so modestly and so widely. A thin line, a chemical anomaly, a sedimentary interruption, and suddenly the ground is carrying evidence of one of the most consequential moments in biological history. There are many such lines. Volcanic ash beds can spread over broad areas and provide time markers across entire regions. Tsunami deposits carry coarse material inland in ways ordinary storms do not. Charcoal-rich horizons can testify to ancient fires. Glacial till announces ice. Evaporates announce drying basins. Red beds imply oxidation. Black shales speak of low oxygen waters, rich in preserved organic matter. Banded iron formations tell of deep changes in the chemistry of the oceans and atmosphere, when dissolved iron repeatedly precipitated as Earth's oxygen balance transformed. These are not messages in words, they are messages in mineral logic. But in some ways they are more reliable than words, because they were not written to persuade anyone. They were written by process. There is something deeply calming about that, though it may not sound calming at first. It means the planet keeps records even when no one is there to watch. It means that events can be reconstructed from traces rather than witnesses. The downside, of course, is that these records are often incomplete, overwritten, tilted, metamorphosed, buried, uplifted, faulted, eroded, or otherwise treated with a degree of roughness that would be considered unacceptable in any normal archive. Earth is not a careful librarian. It is more like an ancient household in which important letters have been stored under carpets, inside walls, and occasionally inside volcanic deposits. Some of the most visually striking messages are impact structures. Meteorite impacts leave scars on the landscape and in the subsurface that can persist for astonishing lengths of time, though not always in forms the casual eye would recognize. Fresh craters are obvious enough. Circular depressions, raised rims, ejecta, shattered rock, melted material. But older impact sites can become buried, eroded, tectonically modified, or only detectable through geophysical patterns, shocked minerals, and subtle geometry in the terrain. When an impact structure is finally recognized, it often feels as though the planet has been carrying a secret punctuation mark for millions of years. A ring in the ground, a buried basin, an unusual gravity anomaly, and then, after enough mapping and drilling, the realization that a violent collision happened here in the deep past. The Chicxulub structure is perhaps the grandest example of a ground message rediscovered. Much of it is buried, but its circular form and physical signatures became one of the key pieces of evidence linking the end Cretaceous extinction to a large impact. The message was there all along, not painted on the surface in an obvious dramatic circle, but encoded in geology, chemistry, and geophysics. That is often how Earth writes at large scale, not in neat outlines visible from a hilltop, but in distributed traces that only assemble into meaning once multiple lines of evidence are brought together. Volcanic landscapes can behave similarly. Lava flows, fissures, tephra blankets, caldera collapses, hydrothermal alteration zones, and gas vents all leave marks that can be read as a long sequence of activity. Some volcanoes preserve histories in layered deposits that record alternating eruptions, quiet intervals, lahars, and shifts in magma chemistry. Others write more directly. A fresh basalt flow across older terrain is about as clear a statement as geology allows. The surface says, this area was recovered by molten rock at a known time, under known conditions, and whatever was here before is now underneath, trying to remain relevant. In places like Iceland, Hawaii, or parts of the East African Rift, the ground really does look as though it has been continuously edited. Deserts are particularly good writing surfaces because they preserve contrast. A shift in colour, gravel cover, crust, or erosion can remain visible across large areas. Dry lake beds record shorelines, contraction polygons, and chemical precipitation patterns. Wind carves dunes into migrating scripts that are beautiful and unreadable in the ordinary sense, but highly informative to anyone studying wind regime and sediment supply. Ancient river channels remain incised or traceable long after the water is gone. Remote sensing has made this even more striking. Satellite imagery reveals buried drainage systems under sand, ancient field boundaries, abandoned roads, walls, and settlement traces invisible from the ground. The landscape becomes a palimpsest, one set of marks written over another, each still partly visible if viewed from the right angle or wavelength. That word, palimpsest, is especially useful here. Originally it refers to a manuscript page reused by scraping or washing away older writing and applying new text. Though traces of the earlier layer remain, the Earth is full of palimpsests. A glacial landscape overprints older river topography. An ancient shoreline cuts across older structures. Agricultural terracing modifies a hillside already shaped by landslides. A city grows over a floodplain, then over earlier settlements, then over buried channels. A desert covers and later reveals stone features. A forest masks old field systems. Nothing is ever just one message. The ground is written on repeatedly, and that repetition is part of why some things seem not to belong. We're often seeing two different times at once. This is especially true in archaeology. LiDAR surveys have transformed our ability to see human modifications of landscapes beneath forest canopies, revealing road networks, settlement grids, terracing, causeways, defensive works, and earthworks in places once thought comparatively empty or simple. Mesoamerican cities, Amazonian earthworks, ancient agricultural systems, and complex settlement patterns have all emerged more clearly thanks to technologies that can peel back vegetation and expose the shape of the land underneath. The effect is almost magical the first time you see it, but the lesson is sober and important. The ground may be carrying far more human history than is obvious on the surface. There is an interesting symmetry in that. Just as geologists learn to read the planet beneath modern appearances, archaeologists learn to read old human intention beneath later growth, collapse, and reuse. In both cases, the surface lies, or at least it simplifies. A quiet hill may be a mound. A field may conceal ditches. A forest may cover roads. A flat plain may preserve the footprint of ancient irrigation. The message is there, but not in the way the eye first receives the place. Nature, though, remains the more prolific writer. Consider fossil trackways. A set of footprints preserved in sediment is among the most intimate messages the ground can hold. Not just that an organism existed, but that it moved here, in this direction, on this kind of surface, with this gait, under these conditions, at this moment of soft sediment before burial and preservation. Trackways collapse time in a way bones do not. A skeleton tells you what something was, A trackway tells you what it was doing. That difference matters enormously. A few prints in volcanic ash, mud, or shoreline sediment can turn an ancient world from static to active. One can almost picture the animal crossing, pausing, changing pace, following another, slipping, turning. It is difficult to think of anything more like a message left accidentally, and yet preserved with extraordinary effect. Some of the earliest evidence of life behaves in a similar way. Stromatolites, layered structures formed through the activity of microbial communities trapping and binding sediment or influencing mineral precipitation, are not messages in any intentional sense, but they are records of life interacting with Earth's surface chemistry on a planetary timescale. They are among the oldest signs that biology was shaping the planet. Their layered forms, often domed or columnar, are the residue of repetition, growth, sedimentation, and mineralization. A stromatolite says, here life was active enough, persistent enough, and chemically engaged enough to leave architecture behind. It is one of the oldest ground messages we have, though it took us a very long time to learn how to read it. This is really the heart of the matter. Messages written in the ground are often only messages in retrospect. They become readable when a method exists to interpret them. Before plate tectonics, seafloor stripes were just odd data. Before impact geology matured, shocked minerals and circular structures were easier to miss or misclassify. Before isotope geochemistry, certain chemical anomalies were invisible as narrative. Before aerial archaeology, many earthworks were only fragments on foot. Before LiDAR, forest-covered landscapes conceal their geometry. The Earth does not wait for our interpretive tools. It records first and lets comprehension arrive later. There are also cases where the message may not be fully understood, even though the mark itself is obvious. Mima mounds, for instance, those low earthen mounds found in certain grassland settings, remain debated in origin. Different mechanisms have been proposed in different regions, including burrowing animals, shrink-swell soil processes, and self-organizing landscape dynamics. The mounds are real, widespread, and visually distinctive. They look as though something arranged them. In a sense, something did. The difficulty is identifying precisely which process, under which conditions, and whether a single explanation fits all occurrences. They're a perfect example of how the land can bear a visible sign long before we have agreed on the handwriting. The same could be said of some polygonal ground in permafrost, patterned bedrock, strange ridge fields, and localized geomorphic forms that look almost too deliberate. It is not that they are supernatural, nor even that they are necessarily rare. It is that their visible order forces a question. What process writes like this? That question is often more interesting than the initial sense of mystery, because it turns the shape into a doorway toward frost action, groundwater flow, tectonic stress, vegetation feedback, sediment transport, or some combination of them all. And once you become attuned to this way of seeing, the Earth looks less blank than before. Bare rock walls are not blank. They preserve deformation, veining, mineral growth, weathering fronts, and fluid histories. Cave interiors are not blank. They preserve drip patterns, growth bands, flooding marks, soot, pigments, and mineral stains. Lake beds are not blank. They preserve varves, those annual sediment layers that can be counted like pages in a very patient diary. Trees themselves, though not the ground exactly, record climate in rings, fire in scars, drought in narrow growth, and disturbance in asymmetry. Nature is continuously making marks, and not all of them need survive equally long to be meaningful. The curious thing is that a true message usually assumes a sender and receiver. With Earth, that relationship is less tidy. The sender is process. The receiver is anyone capable of inference. The meaning is not symbolic, but evidential. A flood does not mean warning in the ground unless a later reader interprets the deposit that way. A charcoal layer does not mean fire until someone identifies it. A geoglyph does not mean ritual or route or territory until it is placed in cultural and archaeological context. The marks exist first, meaning comes second. That sequence is easy to forget because once interpretation settles in, the message can feel obvious. It rarely is. And perhaps that is what makes these ground-written traces so compelling. They exist right at the edge between visible and understood. You can stand in front of them and still not know what they're telling you. A line in a desert, a ring in a plain, a set of bare circles among grass, a mound field, a fossil trackway, a thin clay band at the boundary between worlds, a buried city seen through a laser scan, a stain of mineralization that says fluids once moved here. The land can be eloquent and cryptic at the same time, which is, in its own quiet way, the same feeling that has run through all of these examples from the beginning. Things on Earth that seem not to belong are often not intrusions at all. They are parts of stories whose surrounding context has been lost, hidden, or not yet fully assembled. The message is there, but the language is only partly known. And once you start to see the ground as a recording surface full of traces, one further question becomes unavoidable. What do we make of the places where the land itself seems to preserve a secret so large, so deep, or so persistent that even now it resists a complete reading? Reading marks on the surface is one thing. Reaching the places that produce some of those marks is another. There are parts of Earth that remain difficult not because they are mythical, but because they are physically awkward, chemically hostile, buried under water, sealed under ice, hidden below rock, or spread so far beneath our feet that direct access is barely possible at all. These are the places the planet seems to keep to itself, not in the sense of intention, as though Earth were guarding a diary in a locked drawer, though it does sometimes behave like an old relative who answers perfectly simple questions with a look that suggests you should already know better. What makes these places feel secret is that they resist the ordinary ways humans gather knowledge. We like to walk up to things, measure them, sample them, repeat the sampling, compare notes, and then speak with confidence. Earth is under no obligation to arrange its least convenient truth somewhere near a parking area. That is why some of the most revealing discoveries on this planet come not from what is openly visible, but from places that conceal themselves by depth, pressure, darkness, or inaccessibility. A hidden lake beneath Antarctic ice. A cave system so deep that it has its own weather and its own hazards waiting in the dark. A microbial ecosystem sealed in rock kilometers underground. A trench in the seafloor where pressure becomes difficult even to imagine in any practical sense. A huge structure deep in the mantle, invisible except through the way seismic waves slow down or bend as they pass through it. These are not fantasy settings, they are real parts of Earth, yet they carry that same persistent feeling that has run through all of this from the start. That some things on this planet seem not to belong simply because we have not had much chance to know them properly. One of the clearest examples is the world beneath large ice sheets. From above, Antarctica can look blank in the most misleading way possible, white, cold, broad, and apparently simple, but under that ice is a hidden landscape of mountains, valleys, sediments, rivers, lakes, and active processes. Some of those lakes have been sealed beneath the ice for extraordinarily long periods. Lake Vostok is the one most people have heard of, though it is by no means the only subglacial lake. The point is not just that water exists under kilometres of ice, though that alone already sounds like the sort of detail the planet ought to have mentioned earlier. The point is that this water may preserve chemical conditions, sediments, and microbial activity unlike anything at the surface. An environment physically cut off, pressurized, dark and cold, yet not inert. Not a frozen empty chamber, but a system, and that changes how the mind pictures Antarctica. It stops being a simple cap of ice and becomes a cover. Beneath it lie hydrological networks, moving water, soft sediments, perhaps long isolated microbial communities, and records of past climate hidden in layers and basins we are only beginning to sample with enough care. Drilling into such places is not easy, and it should not be easy. The technical challenge is immense, the contamination risk is serious, the logistics are brutal. Everything about the process reminds you that the hidden place is not volunteering. Yet when scientists do reach these environments, they find that the secret is often not one dramatic revelation, but a collection of quieter truths. Water can remain liquid under pressure and geothermal influence. Microbial life can persist with little light and limited nutrients. Sediments can preserve long records. Entire systems can exist out of sight while still being fully part of the planet's ongoing activity. Deep caves create a similar effect, though in a more intimate and rather less polar way. There are cave systems on Earth that descend so far that the language we use about ordinary underground space begins to feel inadequate. These are not just holes in rock, they are vertical worlds, with shafts, chambers, streams, temperature shifts, gas hazards, and isolated ecologies. The deeper one goes, the less the surface feels like the reference point. Time changes there. Sound changes. Movement changes. The body becomes very aware that the rock around it has been in charge for a very long time. What makes these caves feel secret is not only their difficulty, but the fact that they so often preserve conditions the surface has long forgotten. Water flows through them from distant places. Minerals grow slowly on their walls. Air chemistry varies. Some hold ancient sediments, fossils, or evidence of climate swings recorded in speleothems, those cave deposits that build layer by layer as water drips and leaves minerals behind. Others host life adapted to darkness, low nutrient supply and long isolation. There are caves where sulfuric acid has helped shape the passages, caves with microbial communities living off unusual chemistry, caves where the difference between breathable and dangerous air is not a philosophical question, but a matter of where exactly you're standing. The deeper Earth becomes, the less it resembles an empty basement, and the more it resembles a set of concealed operating systems. Movel Cave in Romania is one of the best reminders of that. Sealed off from the surface for a very long time, it hosts an ecosystem based not on sunlight, but on chemosynthesis. Microbes use compounds such as hydrogen sulfide and methane, and a whole food web is built on that chemical foundation in air and water that would not count as inviting by normal standards. The place feels wrong in the way these hidden places often do. Not wrong as in impossible, wrong as in difficult to fit into the ordinary mental picture of a cave as a dark extension of the surface world. It is not that. It is its own system, and one that remained almost completely out of sight until the right people, with the right methods, went looking. The deep ocean is perhaps the largest category of secret place, simply because it is so extensive and so physically hard to work in. We have mapped the moon in better detail than parts of our own seafloor, which is one of those facts that sounds like a joke about funding priorities, until you remember how much more convenient it is in some respects to look up than down. Water hides things very effectively. It absorbs light, amplifies pressure, carries sediment, and makes every technical task more complicated. The Hadal zone, those trench environments deeper than about 6 kilometers, is especially difficult. Pressure there is not merely high, it is enough to crush the ordinary confidence out of most equipment. Yet those places are not empty. They contain sediments, microbial processes, scavengers, strange animals, chemical gradients, and geological activity tied to subduction, and the movement of plates. What is striking is how often a trench or abyssal plain is treated, in casual imagination, as the end of the map. Beyond a certain depth, the sea becomes a generic dark. But from a scientific standpoint, that darkness contains specifics. Organic matter sinks and is consumed. Faults deform the seabed. Fluids move. Sediments accumulate. Microbes persist. Pressure shapes biology. Chemistry shifts from one layer to another. The deepest ocean is not a blank. It is a place where most of the usual sensory shortcuts fail. and so we mistake lack of visibility for lack of structure. The same is true of brine pools and anoxic basins on the seafloor. These are environments where salinity, density, oxygen levels, and chemistry create boundaries so sharp that the water itself seems divided into different worlds. Brines can sit in depressions like underwater lakes, their surfaces shimmering, their contents hostile to many organisms, yet still surrounded by life exploiting the edges and gradients. Again, the secret is not that these places are supernatural. It is that they are physically hidden and chemically extreme enough to remain conceptually distant even after discovery. We know they are there, and still they feel like something the planet forgot to put in the brochure. Then there is the deep biosphere, which remains one of the most quietly disruptive ideas in modern Earth science. For a long time, life was imagined mainly as a surface affair. Soil, sea, sunlight, weather, forests, rivers, and the upper layers of sediment where nutrients and oxygen seemed available enough to support the expected cast of organisms. But microbes exist far below that zone, in rock pores, fracture waters, buried sediments, and crustal environments where energy is scarce and conditions are nothing like the bright, productive surface world. This is not the sort of discovery that arrives with a spectacular skyline. It arrives with cores, fluids, careful contamination control, slow measurements, and the uncomfortable realization that the habitable planet extends downward much farther than we once thought. And that creates a very interesting kind of secrecy. These organisms are not rare because they are hidden on purpose. They are hidden because their world is physically inaccessible, and because their way of living is easy to overlook. Slow metabolism does not announce itself dramatically. A microbe kilometers underground, drawing energy from geochemical reactions in rock and water, is not trying to impress anyone. But it does force a reconsideration of what counts as a living environment. The surface is not the whole stage. Much of the play has been taking place below it all along. If the deep biosphere makes the interior of Earth seem more inhabited than expected, the mantle makes it seem much less simple. No one is visiting the mantle directly. We infer it. We melt pieces of it in laboratories. We study what volcanic rocks bring upward. We use seismic waves to build images of structures deep below. And those images keep reminding us that Earth's interior is not a tidy layered cake in the cartoon sense. There are deep mantle features, including vast regions under Africa and the Pacific, where seismic waves travel unusually slowly, that suggest large compositional or thermal anomalies. Exactly what these structures are, how stable they have been over geological time, how they interact with mantle convection, and how much they influence volcanism and the long-term cooling of the planet are not fully settled questions. That is a very particular kind of secret. We know something is there because waves passing through Earth behave differently than expected. We can model it, debate it, compare interpretations, and gradually improve the image. But we cannot simply lower a camera into the lower mantle and have a look around, which is probably just as well for the camera. So the deep Earth remains a place of indirect knowledge, where hidden structures are real and important, but only partly visible through their effects. This is often how the planet keeps its most consequential secrets, not by making them invisible, but by making them legible only through distortion, echo, heat flow, chemistry, and the occasional rock that returns from depth carrying incomplete news. Buried landscapes also belong in this category. There are ancient river systems under deserts, under continental shelves, and beneath modern sediments. There are mountain ranges beneath ice. There are impact structures hidden below younger deposits. There are old coastlines drowned by rising seas and glacial valleys concealed under till and later erosion. In each case, a former surface survives beneath the present one. Earth does not erase as completely as it first appears. It covers, it overprints. It shifts the visible layer and leaves older topographies beneath it. With remote sensing, seismic reflection, drilling, gravity measurements, and other tools, we're increasingly able to detect these buried worlds, and when we do, they often make the present landscape seem thinner than it looked before. Beneath a plain there may be a canyon, beneath an ice sheet, a lake. Beneath a shallow sea floor, a river valley older than the coast above it. This is one reason secret can be a practical word even in science, provided we do not use it too theatrically. The secret is often simply that one layer of Earth is hiding another. The surface gives an incomplete account because it is only the latest version. Once you know that, the planet starts to look less like a stable arrangement of visible places and more like a stack of worlds, only one of which we inhabit directly at any given time. Some of the most dramatic hidden places are those that are active while remaining mostly unseen. Magma reservoirs beneath volcanoes are an obvious example. We do not look into them directly. We infer them from deformation, seismicity, gas emissions, heat flow, petrology, and eruption history. Yet these concealed bodies of melt and crystal-rich mush govern eruptions, uplift, hydrothermal systems, and volcanic hazards that can affect millions of people. The public image of a volcano is usually the mountain itself, the crater, the lava, the ash. But the real system extends beneath the visible structure into plumbing networks, storage zones, rising gases, and migrating magma pathways. The mountain is the surface expression of a much larger hidden machine, and even when a volcano seems quiet, the concealed part may still be in motion. Fluids can move, gases can accumulate, ground can deform by centimetres that only instruments detect. Small earthquakes may map the travel of magma or the response of brittle rock to changing pressure. Again, secrecy here is not mystical, it is structural. The controlling processes occur below the line of sight. By the time the visible event happens, much of the story has already unfolded in the dark. The same could be said for faults. A fault line on a map is a wonderfully misleading simplification. Real faults are zones, networks, histories, and behaviours distributed through rock volumes that can remain locked, creep, pulse, rupture, and heal over time. Stress accumulates invisibly. Fluids alter friction. Mineral transformations occur. Tiny earthquakes whisper before large ones speak. Much of the most important work of tectonics happens out of view. We only notice the dramatic end of the process because that is when buildings shake and cups fall off shelves. But the fault has been busy long before that, carrying a hidden record of stress, strain, and incomplete release. This is really what makes these places feel as though they do not fully belong to our ordinary understanding of Earth. They are not absent from the planet. They are absent from the immediate human experience of it. We live on a thin, accessible layer and then construct a mental model of the whole from there. Hidden lakes, deep caves, trenches, buried landscapes, deep biospheres, mantle anomalies, magma systems, and fault zones all expose the limits of that method. They remind us that the Earth we walk on is not the Earth in full. It is the top surface of a much thicker and more complicated arrangement. There is also a practical humility in this. Every time technology improves, another concealed part of the planet becomes a little less secret. Radar sees through ice. LiDAR sees through forests. Seismic imaging sees through rock in its own indirect way. Autonomous submersibles map deep sea floor. Deep drilling samples sediments and crust. Geochemistry infers hidden fluids and past temperatures. None of this abolishes mystery. It just redistributes it. The hidden place becomes better described, and in the process new questions appear. What lives there? How long has it been isolated? What formed this structure? How stable is it? How does it connect to the surface? The more we uncover, the more precise the secrecy becomes. And perhaps that is the most interesting point of all. The planet does not merely keep places from us, it keeps categories from us. A lake under ice is not quite like our ordinary idea of a lake. A cave ecosystem sealed from sunlight is not quite like our ordinary idea of a habitat. A mantle structure larger than continents, but visible only through wave behaviour, is not quite like our ordinary idea of a place at all. We keep trying to fit these hidden environments into familiar boxes, and they keep resisting slightly. They belong to Earth, certainly, but they do not sit comfortably inside the Earth we carry around in our heads, which is a useful tension to carry forward, because after enough strange materials, unlikely life, misplaced objects, hidden patterns, ground-written records and secret places, the problem begins to shift. The puzzle is no longer just why certain things seem out of place. The puzzle becomes what we mean by place in the first place, and how much of that feeling of not belonging comes not from the discoveries themselves, but from the categories we insist on using to sort them. By the time you've seen enough strange rocks, unlikely microbes, awkward artifacts, repeated patterns, cryptic marks in the land, and hidden places beneath the surface, a slightly uncomfortable thought begins to settle in. Perhaps the problem is not only that the planet contains things which seem out of place. Perhaps the deeper problem is that we have very strong ideas about place. We like to know where things belong. We like categories, containers, labels, shelves, and boundaries. We like to think some things are geological, some biological, some historical, some accidental, some natural, some made, some ordinary, some anomalous. Once those labels are attached, we become very attached to them in turn. The moment something refuses to sit quietly in the assigned box, it feels not merely surprising but mildly impolite. That reaction is understandable. It is also one of the reasons the phrase "doesn't belong here" can be so revealing. It sounds like a statement about the object, but it is often a statement about our framework. We notice mismatch. We notice category failure. We notice when the thing in front of us does not line up with the shelf label we had already written. In that sense, belonging is not just a property of the world. It is a negotiation between the world and the way we organise it. Science depends on that organisation more than we sometimes admit. Classification is not a minor administrative habit. It is a core way of thinking. We separate igneous from sedimentary, reptile from mammal, artifact from geofact, signal from noise, natural from anthropogenic, deep from shallow, ancient from recent. We do this because it works remarkably well most of the time. Categories help us see structure. They make comparison possible. They allow prediction. They let us say useful things quickly. If a rock is basalt, that already tells you something. If an organism is archaeal, that tells you something else. If a layer is glacial till rather than river sediment, that changes the whole story of the place. But every category comes with edges, and edges are where the trouble starts. Because nature is not especially interested in our need for tidy sorting. It produces transitions, hybrids, feedbacks, recycled materials, remobilized chemistry, organisms living by partnership, objects displaced from original contexts, and landscapes overwritten so many times that one process shades gradually into another. We, by contrast, often prefer the clean version. Here is the rock, here is the metal, here is the fossil, here is the tool, here is the life form, here is the environment it belongs in. That is a deeply convenient way to think until the world begins sending back cases that look as though they were assembled specifically to annoy convenience. Consider something as basic as a shoreline. It seems obvious enough. Sea on one side, land on the other, a border anyone can point to while feeling organised. And yet shorelines move, flood, retreat, migrate, split, drown, and expose older surfaces. Tides complicate them daily. Storms rearrange them seasonally. Sea level change redraws them over geological time. Wetlands blur them. Estuaries dissolve them altogether into gradients of salt, sediment, current, and ecology. The shoreline belongs nowhere stable. It is an edge that performs instability for a living. And that is only one familiar example. Earth is full of such blurry boundaries, pretending, at a glance, to be firm. The same is true of time. We speak about past and present as though they are cleanly separated, but much of Earth is built from the persistence of the past inside the present. Ancient zircons in younger rocks, fossil shorelines above modern coasts, ice-preserving atmospheric records from climates long gone, buried soils under lava flows, Deep fluids isolated for immense periods but sampled today. Old carbon cycling through new ecosystems. The planet keeps carrying earlier states forward into later ones. A thing found now may belong chemically to one age, structurally to another, and contextually to a third. It is very difficult to place that tidily on a single shelf. This is one reason anomalies tend to feel more disruptive than they really are. They expose how many of our categories rely on ideal cases. We imagine a biological organism in a biological setting, a geological object in a geological setting, a human artifact in a historical layer matching its manufacture. A metal deposit formed in a pathway we can model from start to finish. A pattern explained by one mechanism, a hidden place belonging to one domain only. Then the real world arrives and says, not quite. The organism depends on geology. The artifact is in a redeposited layer. The rock contains biological traces. The metal required microbial mediation. The pattern results from several interacting processes. The hidden place is both hydrological and biological and chemical at once. And suddenly belonging begins to look less like a fact and more like a temporary administrative decision. It is worth being clear that this does not mean categories are useless. Quite the opposite. They remain among the best tools we have. The mistake is only in treating them as final rather than functional. A useful category helps us navigate. A rigid one begins to mislead. The planet is happy for us to use maps. It is less willing to become identical to them. Biology gives some of the best examples. For a long time, life itself was sorted into a relatively limited set of expectations, built around visible organisms and familiar metabolisms. Plants photosynthesize, animals eat other things, fungi decompose, bacteria do various useful and inconvenient tasks in the background. Then deeper study revealed life living on sulfur, iron, hydrogen, methane, radiation-driven chemistry, symbiosis so intimate it blurs the line between organism and ecosystem, and survival strategies involving dormancy, desiccation, or long-term persistence in places that seemed scarcely habitable at all. It was not life that failed to belong. It was our original definition of a proper living environment that proved too narrow. There is a similar problem in geology whenever we talk about what a rock should contain. That word should is often where trouble enters. It usually means that under the conditions we understand best, with the models currently most accepted, the mineral phase or chemistry in question is unexpected. That is a reasonable statement, but over time it can harden into something stronger, as though the rock itself had violated an agreed standard. In reality, it may simply have recorded a set of conditions we had not yet included, or preserved a history longer and more complicated than our first reading aloud. The rock belongs to the Earth perfectly well. The issue is that it belongs to an Earth more varied than the simplified one in our heads. Archaeology faces its own version of this every time an object seems too early, too advanced, too distant from its expected cultural context, or too difficult to fit into a linear progression. Humans have a habit of treating history like a staircase, but real history is full of loops, local brilliance, forgotten methods, preserved outliers, and technologies that appear advanced only because the surviving record around them is so incomplete. When an object appears not to belong, the question is often not whether the object is impossible. It is whether our timeline has been flattened too much. Flattening is a quiet habit of modern thought. We summarize because we have to. We tell broad stories because no one can carry every detail all at once. Early Earth was hot, then it cooled. Life emerged, technology advanced, continents moved, seas changed, oxygen rose, civilizations developed. These are all fair enough as broad lines, but broad lines produce broad expectations. Then a crystal, a microbial ecosystem, an artifact, a geochemical trace, or a hidden structure arrives, and reminds us that broad lines are not the same thing as full accounts. This is why belonging can become such a troublesome word in science. It often sneaks in two assumptions at once. First, that the object or phenomenon should be judged against a stable background model. Second, that the model is complete enough to decide the matter confidently. Sometimes both assumptions are justified. A modern steel nail does not belong in an undisturbed Bronze Age layer. That is a straightforward problem. A fossil shell does not belong in lava that crystallized yesterday. Again, fair enough. But many cases are less neat than that. A mineral stable at great depth in a mountain rock near the surface may look misplaced until deep burial and later uplift enter the story. A microbial community in poisonously acidic water may look impossible until metabolism, membranes, and evolution are given their proper say. The issue is not the thing itself. The issue is that our quick version of where such a thing belongs was built from examples that were too comfortable. There's also a human tendency to confuse rarity with unbelonging. If something is uncommon, isolated, or difficult to explain, it is easy to start speaking as though it arrived from outside the normal order of things. But rare is not the same as foreign. A black diamond with an odd origin is still part of Earth's material story, even if that story remains contested in detail. A hidden ecosystem under Antarctic ice is still Earth life, even if it does not resemble the environments we know best. A pattern in the ground we cannot fully explain is still the result of some earthly process or combination of processes, even if we have not yet sorted them out. The temptation to exile the strange from the ordinary is strong. It is also often unhelpful. Perhaps the simplest way to put it is this. Belonging sounds spatial, but it is really explanatory. We say something belongs when we feel we know how it fits. We say it does not belong when the fit is missing. That missing fit can feel dramatic, but it is often just a gap in understanding rather than a breach in reality. Earth did not suddenly produce a foreign intruder. It produced a fact for which our surrounding explanation is still under construction. That may seem like a small distinction, but it changes the mood of the entire problem. If the odd thing truly stands outside nature, then the only options are panic, fantasy, or very confused paperwork. But if the odd thing belongs to nature while escaping our current categories, then it becomes not a threat to knowledge but an invitation to improve it. The anomaly stops being an insult and becomes a clue, and clues are often found precisely where categories overlap. Think about hydrothermal vents. Are they geological features or biological habitats? Obviously both. Think about cave formations with microbial influence. Geological or biological? Both again. Think about ore deposits shaped partly by fluid flow, partly by rock chemistry, partly by microbial mediation in some environments, and later transformed by tectonics. Geological, chemical, biological, historical, unhelpfully, all of the above. The most interesting places on Earth are often the ones that sit across several domains at once. We only experience them as difficult because institutions, textbooks, and habits of thought like cleaner divisions than the world provides. This overlap appears even in the language we use for discovery. An object is out of context. A signal is noise. A species is extremophile. A deposit is anomalous. A landscape is unusual. These labels are useful, but they are all relative to a baseline, and that baseline is shaped by what we have already seen, sampled, measured, and taught. Once enough new evidence accumulates, yesterday's anomaly becomes today's special case and tomorrow's ordinary example. That process has happened repeatedly. Continental drift was once deeply inconvenient. Chemosynthetic ecosystems were once unimaginable to many non-specialists. The deep biosphere was once scarcely part of the common picture of life at all. Each now belongs comfortably enough to science, though not because the world changed to become more reasonable. We changed our framework. There is something quietly reassuring in that. It means science is not a machine for defending categories at all costs. At its best, it is a machine for using categories until they stop working, then revising them. That revision can be slow, argumentative, and full of people defending older language a little longer than necessary, because scientists are human and therefore attached to their favourite ideas just like everyone else. But the system does have a long record of gradually letting the world win. Even so, the emotional residue of belonging remains powerful. We feel more unsettled by an object that looks placed than by a stone shaped by erosion. We are more disturbed by a pattern that resembles design than by one we immediately connect to known process. We are more likely to dramatize a life form in an extreme environment than a strange chemistry in a granite, because the first feels like a breach in our idea of where living things belong. Belonging is not just scientific, it is psychological. We are pattern-making creatures who like the world sorted into neighbourhoods, and perhaps that is why Earth remains so effective at surprising us. It is not merely that there are unknown things, it is that the unknowns often arrive disguised as category errors, a metal where it should not be, a creature where it should not live, a device before it should exist, a signal where there should be randomness, a hidden lake where there should be only ice, a deep structure in the mantle that behaves unlike the simple diagrams. The surprise comes from violated expectation, and violated expectation always feels more personal than an ordinary absence of knowledge. We are not just learning something new, we are being corrected. Corrections, if taken well, are extremely useful. They loosen the grip of too simple stories. They also force a more mature understanding of belonging itself. Maybe belonging is not about fitting one category cleanly, but about participating in a process, a history, or a set of relationships. A mineral belongs not just to a rock type, but to a pressure temperature path. An organism belongs not just to a habitat, but to a web of chemistry and adaptation. An artifact belongs not just to a date, but to a human tradition of making, use, and preservation. A pattern belongs not just to a shape, but to the forces that generate repetition. A hidden place belongs not just on a map, but in the larger functioning of the planet. Seen that way, many anomalies become less like misplaced items and more like improperly summarized ones. The summary was too short. The object was too rich. Naturally, there was friction. There is also an ethical kind of modesty in this. It asks us not to assume that the familiar slice of Earth available to everyday human life is the standard by which everything else should be judged. The surface conditions we prefer are only one local arrangement among many. Dry, dark, saline, acidic, pressurized, buried, ancient, intermittent, chemically odd, isolated, slowly active. These are not deviations from the real planet. They are the real planet too. If something seems not to belong because it sits outside our comfort zone, that says more about comfort than about Earth. That thought loops back nicely to the very start of all this. A thing on Earth that appears not to belong here often turns out to belong to a version of Earth larger than the one we began with. A deeper Earth, an older Earth, a chemically stranger Earth, a more interconnected Earth, a more patient Earth, a more biologically stubborn Earth. The discovery expands the frame, and once the frame expands, the anomaly relaxes slightly. It has not become less strange. It has simply found its place in a bigger story. Of course, bigger stories create their own difficulty. Every time we widen the frame, we also become aware of how much remains outside it. The categories improve, but they do not stop being provisional. The maps become better, but they do not become final. The more carefully we define what belongs, the more edge cases appear. This is not failure. It is what a living science looks like when studying a planet that has had billions of years to complicate itself. So the real trouble with belonging is not that the world contains things that defy all order. It is that the order we build must remain flexible enough to survive contact with reality. Too loose, and nothing means anything. Too rigid, and the next discovery breaks the shelf. The best response is not to abandon categories, nor to worship them, but to treat them as working tools, useful, revisable, and always slightly smaller than the planet they describe. And once you accept that, the entire tone of the mystery changes. The odd material, the misplaced object, the hidden signal, the impossible seeming life form, the secret place under ice or stone or sea, none of these need to be treated as intruders anymore. They become reminders reminders that Earth is not fully captured by our summaries, not exhausted by our measurements, not finished simply because we have named many of its parts. The feeling that something does not belong may be, in the end, one of the most productive feelings science has, because it is so often the first sign that the world is about to tell us more than we were ready to hear. And that may be the most useful place to arrive, because once you stop treating Earth as a finished catalogue and start treating it as an ongoing investigation, the question changes again. It is no longer simply why certain things seem out of place. It becomes what else the planet has not yet made easy for us to see. And the answer, rather inconveniently for anyone who likes complete answers before bed, is probably quite a lot. This is not because Earth is unknowable in some grand mystical sense. It is because it is old, layered, active, and much larger than the slice of it we experience directly. We know an extraordinary amount about this planet compared with any generation before us. We can date crystals billions of years old. We can trace past climates through ice, mud, pollen, and isotopes. We can image structures deep in the crust and infer even deeper ones in the mantle. We can sequence DNA from organisms no one can see with the naked eye. We can map trenches, monitor volcanoes, track tectonic strain, and detect tiny shifts in atmospheric chemistry. That is all real progress. It is also not the same thing as being finished. The feeling that Earth still has things it has not told us comes from a very simple fact. Most of the planet is not conveniently available for inspection. The deep ocean is hard to reach. The deep crust is harder. The mantle is effectively out of reach except through indirect evidence and the occasional material carried upward by volcanic processes, like an unhelpfully edited postcard. Ice sheets hide landscapes. Sediments bury older surfaces. Forest canopies hide archaeological traces. Caves extend beyond easy access. Microbial worlds remain invisible until sampled, and even then many refuse to grow politely in a laboratory. There are places on Earth where our knowledge is detailed and confident. There are many others where it is stitched together from hints. That matters because hidden systems are often the ones that surprise us most. The surface world gives an impression of familiarity. We walk on it. We build on it. We divide it into countries, roads, farms, parks, and well-reviewed hiking routes. Beneath that, however, there are fluid pathways, buried faults, mineral changes, ancient sediments, isolated waters, microbial communities, and thermal gradients carrying on with very little concern for whether anyone has written them up properly. The Earth beneath everyday life is not just a support structure. It is a working system, and we are still learning its habits. Take something as basic as the origin of life. This is not a small loose end. It is one of the largest. We know life has existed on Earth for a very long time. We know early environments were chemically and physically different from those of today. We know certain minerals, hydrothermal systems, wet-dry cycles, and energy gradients may have helped push chemistry toward biology. We know ribosomes and cells did not simply appear fully assembled like flat-pack furniture, with all the screws already sorted. Somewhere on this planet, under conditions no one can replay in exact detail, chemistry crossed into heredity, metabolism, and self-maintaining systems. That happened here. And yet the full path remains unresolved. Not because nothing is known, but because enough is still missing that the exact route from non-living chemistry to the first living systems remains one of Earth's greatest unfinished stories. There is something oddly grounding about that. The biggest mystery on Earth is not necessarily hidden in the deepest trench or the strangest cave. It may be hidden in chemistry that happened billions of years ago and left only fragmentary clues. That means the planet has not merely kept from us some unusual minerals or a few difficult ecosystems. It has withheld, or perhaps simply failed to preserve in neat enough form, the complete account of how its own biosphere began. One can hardly blame it. 4 billion years is not ideal for careful record keeping, and origins are not the only place where the record thins out. The history of oxygen on Earth, for instance, is still more complicated than the school version. The broad outline is familiar enough. Early Earth had little free oxygen in the atmosphere. Photosynthetic organisms evolved. Oxygen began to accumulate. The planet changed. Fair enough as a rough sketch. But the timing, feedbacks, local conditions, ocean chemistry, atmospheric swings, biological responses and repeated transitions are far richer and more uneven than a simple line on a diagram suggests. There were false starts, local oxygen oases, long delays, and profound planetary consequences still being worked through in detail. The rock record tells us a great deal, but not everything with the tidy clarity we might prefer. Earth, on this point as on many others, appears to have provided the important pages and misplaced several key footnotes. Then there are the unknowns of the deep carbon cycle, which sounds at first like the kind of phrase designed to clear a room at a dinner party, but is actually deeply important. Carbon moves through the atmosphere, oceans, soils, organisms, sediments, crust, and mantle over timescales ranging from days to hundreds of millions of years. We understand much of that movement in broad terms, yet there are still real questions about how much carbon is stored deep within Earth, how it moves through subduction zones, how it is released by volcanism, how microbial life influences it in the subsurface, and how these long cycles have shaped habitability over geological time. Carbon is not just the basis of life and a modern climate concern. It is part of the planet's deep machinery. And that machinery is still not fully mapped in motion. The same can be said of water. Surface water is familiar enough. Rain falls, rivers flow, ice forms, oceans misbehave near coastlines. But the deeper water story remains incomplete in fascinating ways. Water is carried into Earth's interior in minerals, released during metamorphism, influences melting, weakens rock, changes eruption style, and may be stored in large quantities in forms that are chemically bound rather than sloshing around in underground seas with dramatic lighting. We know enough to say the deep water cycle is real and significant. We do not yet know every detail of its scale, variability, or long-term behaviour. In other words, the planet still has not fully explained where all its water goes when it is not being obvious about it. And biology, for all our progress, is still full of blank spaces. New species are described every year, especially among insects, fungi, microbes, and deep-sea organisms. That alone is humbling. We are not merely refining the last decimal place of knowledge. We are still discovering that certain forms of life exist at all. Entire microbial lineages have emerged through genetic methods from environments we barely understood before. Deep ocean surveys keep revealing animals, symbioses, and behaviours that expand the living map of the planet. Soil communities remain staggeringly complex. Fungal networks are often discussed with a little too much enthusiasm for metaphor. But even after one removes the more theatrical claims, the diversity and ecological importance of what happens in ordinary ground under ordinary feet is remarkable. A walk in a field is, from the microbial point of view, a traffic incident passing over one of the most intricate biological systems on Earth. There is also the matter of extinction, both past and present, which complicates the idea of what Earth has not told us, because some of what it has not told us may be gone. Species disappear before they are described. Ancient ecosystems vanish with only partial traces. Climatic shifts erase habitats, redistribute ranges, and scramble the evidence. The fossil record is an archive, but not a complete census. It tells us marvellous things about ancient life, yet it preserves only a filtered sample of what existed. Soft-bodied organisms are underrepresented. Entire environments preserve poorly. Many species leave no direct descendants and no clear memorial beyond a few impressions, chemical traces, or bone fragments. The planet has not only kept secrets through concealment, it has also lost some of its own evidence through the ordinary rough handling of time. This becomes especially clear with mass extinctions and rapid environmental shifts. We often identify the broad trigger or timing, then spend decades arguing about the details. How fast did ecosystems collapse? Which species were resilient and why? How did ocean chemistry change locally versus globally? What happened in the years immediately after a major impact or a pulse of flood basalt volcanism? How patchy was survival? How quickly did recovery unfold? The more closely we look, the less these events resemble a single switch being flipped, and the more they resemble complicated, staggered, regionally variable cascades. Earth gives us the outline in thick strokes, and leaves us to work out the texture with whatever evidence survived. Then there is the ongoing business of the planet's interior, which remains far less settled than people often assume. Plate tectonics is a triumph of explanation, but it is not the end of explanation. We know plates move, we know crust forms and is destroyed, we know subduction, seafloor spreading, and mantle convection are part of the story. Yet the fine detail of how mantle plumes behave, how slabs interact with deep structures, how continents assemble and break apart in recurring supercontinent cycles, how stress reorganizes through plate boundaries, and how the core and mantle exchange heat over immense timescales is still under active investigation. This is not a sign of weakness in the theory. It is a sign that the basic framework is strong enough to support deeper questions. The Earth has given us the rules of the game, and is still keeping some of the advanced tactics to itself. Even earthquakes, for all the instruments pointed at them, continue to contain difficult unknowns. We can identify faults, measure strain, map rupture zones, and understand broad conditions for seismic activity. Predicting the exact timing of specific large earthquakes remains beyond us. Faults do not announce themselves in a well-mannered queue. Slow slip, fluid pressure, rock friction, stress transfer, historical ruptures, and deep structural complexity all matter. The result is that one of the most consequential and studied processes on Earth remains resistant to the kind of simple foresight people naturally want from science. That is frustrating, but it is also clarifying. The planet is not hiding earthquake timing out of spite. It is behaving through systems that remain too nonlinear, too buried, and too variable for easy certainty. Climate offers a different version of the same challenge. We understand the fundamentals of greenhouse gases, radiative forcing, feedbacks, circulation, and human influence extremely well. And yet Earth's climate system, especially when considered across deep time and through regional effects, still contains areas of active research. Paleoclimate records keep refining our sense of past extremes, tipping behaviour, ocean circulation changes, drought persistence, ice sheet instability, and ecosystem response. Ancient climates sometimes reveal combinations of temperature, carbon dioxide, vegetation, and ocean chemistry that push us to improve models. The planet's past remains one of our best laboratories for understanding its future, and it continues to provide results that are useful precisely because they are not all fully anticipated. There is also a quieter category of unknowns that deserves more attention, the things Earth is telling us that we do not yet know how to hear properly. This has happened again and again. Background seismic hum became informative. Ancient DNA transformed the reading of fossils and past populations. Satellite remote sensing uncovered hidden landscapes, methane leaks, ice dynamics, and patterns in vegetation and geology invisible from the ground. Isotope systems, once too subtle to matter, became central tools. Machine learning is now helping identify structures in huge geophysical and ecological data sets that might otherwise remain overlooked. The planet may not only be keeping secrets, it may be speaking in formats we only recently developed the tools to read. That is a useful thing to remember whenever someone says the world is mostly known now. It is known in some ways, and not in others. We have named a great many things. Naming is not the same as understanding. We have measured many patterns. Measuring is not the same as fully explaining. We have discovered hidden places. Discovery is not the same as exhaustion. Some of the most exciting work in Earth science now is not happening because we have run out of mysteries, but because the mysteries have become more precise. The broad unknown becomes 10 specific unknowns, each with instruments, arguments, samples, and one overworked research team trying to make sense of conflicting results. And perhaps that is the most reassuring answer to the whole question. What Earth still has not told us is probably not one giant theatrical secret waiting behind a curtain. It is thousands of smaller, real, stubborn unknowns distributed across chemistry, life, climate, deep time, hidden habitats, buried structures, planetary cycles, and the origins and limits of habitability itself. Some of these will resolve into ordinary explanations that simply took a while to assemble. Some will alter major parts of our understanding. Some will turn out to be weaker puzzles than first hoped. Others will open entirely new fields and then, in the best scientific tradition, immediately become complicated. That means the strange thing on Earth that appears not to belong may be one of the most valuable kinds of clue we have, not because it points outside nature, but because it points beyond the current edge of the map. It tells us where the framework is thin, where the category is too rigid, where the process is missing steps, where the archive has gaps, where the instrument needs improvement, where the model needs pressure, and where the planet remains larger than our summary of it. There is a nice humility in ending there. Not the grand sort that announces itself and expects applause, but the practical sort. The kind that admits the earth under our feet is not merely familiar ground with a few unusual corners. It is an active, ancient system still capable of surprising the people who study it most carefully. The stones have not finished reporting. The deep biosphere has not finished emerging into view. The oceans are not done giving up hidden habitats. The crust and mantle are not done complicating their own histories. The fossil record is not complete. The archaeological record is patchy. The climate archive is still being read. The first origin of life remains unresolved. The last undiscovered species is nowhere in sight. And that is probably as it should be. A fully explained Earth would be a much less interesting place to inhabit, though perhaps a slightly more convenient one for planners, surveyors, and anyone trying to write a tidy textbook. But the real planet has never been especially tidy. It is layered, adaptive, eroding, recycling, erupting, dissolving, freezing, subducting, oxidizing, mutating, and preserving scraps of itself in whatever form survive the rough journey forward. We get to read those scraps and gradually improve our account. That is not a bad arrangement, even if it does mean the world occasionally answers a simple question with several thousand pages of follow-up. So the next time you hear that something on Earth seems not to belong here, it may be worth hearing the phrase a little differently. Maybe it means not that the thing is in the wrong place, but that our understanding is still too small for the place it belongs to. And if tonight's wandering through strange materials, hidden life, misplaced objects, secret structures, and unfinished explanations has done anything useful, perhaps it is simply this. It has made the planet feel a little less settled, a little more alive with unresolved detail, and a little more honest in its complexity. Which, for a world we often treat as familiar, is a rather comforting thought. The ground beneath us is not just old. It is still in the middle of telling its story.